Okay, good morning, everybody. Let's start our third class. Uh, and Professor Choi, thank you very much for the course and to attend the students during today, yesterday, and on Monday. Thanks a lot. And we can start again now, the third class. Please.
Thank you everyone to come again. So let's continue. Actually, it was supposed to finish it with sample preparation, but still left. I want to continue. Yesterday we finished it with the NMR protocol. Yeah. Most important one is two things. Yeah. NMR protocol is we are using deuterium solvent at the end anyway. Yeah. Deuterium solvent. Is deuterium solvent? Why not? We have to use deuterium solvent as an extraction solvent. Then, if you extracted the deuterium solvent, then we can apply to NMR without any evaporation or reconstitution with your NMR solvent. Then we can reduce the steps, which means reducing step is you can reduce the chance of compounds to be degraded. That was my point. Then I have a question. Yes, here CD3OD is equivalent to the methanol, and D2O is equivalent to water, which means, as I said yesterday, there is no best extraction solvent to extract everything from the material, but based on my experience, 50% methanol can be starting. Then here is why I have to use, instead of water, potassium buffer. The buffer, all the protocol from now on, your students will meet any kind of a protocol, every kind of a protocol. Of course, you have to follow the protocol, but sometimes, not sometimes, you don't have to remember protocol because you have a sheet. You follow the protocol, no problem. You have to understand why they have to use, why exchange is, why I have to use buffer. Yeah, pH. Animal chemical shield. If you do one time animal measurement, actually you don't need a buffer. But you have to, but you have a 100, 1,000 sample. For example, one signal is coming out 1 ppm in animal spectrum. Tomorrow, because of the pH in adjustment, is shifted 1.1 ppm. Of course, it's one spectrum. You can have your own tolerance to accept it. Thousands of spectra, 1.1, 1.2, 0.9, 0.4, something like this one is a problem because at the end, I want to remind you, modern metabolomic profiling, you will use statistics. Then chemical shift is a variable. One time it's 1. Second time, 1.1. The chemical variable is different. Like sometimes I'm calling Fatima. Sometimes I'm calling Maria. This is different. Of course, if I have a very nice relationship with one, she will accept it. But if someone calls differently, different compounds, that's all. Then animal chemical shift, yeah, is always most important factor to change the chemical shift is the pH. Right? One example is if you do citrus, you like it, orange or lemon, when you extract the citrus itself, it's already acidic because there are a lot of citric acid there. But if you extract another part, it's not, there's no less citric acid, pH is changing. So that's why we want to put the pH, the buffer. Is it clear? After that, now is here. 0.7 or something like that. But more or less nowadays, if you are using cryo, how much you need the plant material, more or less dry weight, 10 to 30 milligrams, very fine. And 50 milligrams is a really small one. But what's the problem of this? And always, if you have a if you have a protocol, you have to think about what's the problem. That is really important. What is the problem of this one? It's perfect. There is no perfect protocol. Problem. So so-called this one is a direct deuterium extraction method. Deuterium is expensive, so that's why I use 30 milligrams. No? The problem is if your compound is very low amount, there is a limitation, 30 milligrams. I cannot increase. Because if you increase, you have to increase the deuterium solvent. Anyway, concentration should be same. Always why we have to evaporate and reconstitute because we want to increase the solvent. Increase uh, the concentration. Now I extracted 1 kilogram, for example, and then I dried up, I added 1 milliliter, which means it's your compound is increased. But this one is, there's no evaporation, no step, process. Then it's a very general question. Now, 30 milligram I extracted, NMR is not very much sensitive. But then I can detect only major compound, plant glucose sucrose, like a plant hormone or some minor secondary metabolites. Probably you cannot detect it in the animal. The question is, how dare I say I play it's a metabolomic because metabolomic is put up all metabolites. It's the same to as a mass spec. How? There is a limitation of the number of metabolites. Even it's not metabolites, it's not animal. But then you are doing mass spectrum, also you have a limited metabolites to be extracted, detected. 30,000 chemical, NMR probably 20 or 30, or maximum is 100, mass maybe it's 200 something compounds. How can be sure? So you are detecting only you identify 1% of 1 or 2% metabolites, but you are claiming you are doing all metabolites. It doesn't make any sense. Think about why, and not why. What kind of excuse behind we have? So that's why I gave first lecture this week, biochemistry or biosynthetic pathway. If you know the routine kind of a flavonoid, which means you already learned it. Flavonoid precursor is a charcoal and phenylpropyl and phenylalanine and shikimate. Now it's all connected one, which means this protocol, of course, this one is not perfect method for metabolomics. Once you have a final product, it's all linked in the biosynthetic pathway. Probably you found the routine change, routine change. You have to look for phenylalanine or others by other methods. It's kind of a first step of this. Do you understand? Of course, one day we have a very nice method to get 30,000 chemicals. And second one is now is the Mateus. Yesterday you gave a very impressive presentation. Ideal metabolomic is you show DIA analysis. But please think about these cases. Now, if you are doing blood sample, and you are doing doping test, right? So from blood, you want to detect the heroin or whatever. Now you claim it based on DIA or mass spectrum analysis. If you claim it, oh, you take a heroin, can it be used in the court? Don't go because now it's actually they have a lot of nice lawyer, whatever. They will bring all the That's the 4 years. Oh, this is the methodology. Might be limitation. Maybe it can be misinterpreted. Whatever. It's not only methodology animal say. So that's why it still is provided. We sacrifice some accuracy procedure, and we have a raw data. Raw does not mean it's our laziness. Because of our laziness, it's because it's kind of in the middle, the step of in the middle. We have to do another method. That was it's kind of a message you understand. Next, analytical decision is please think about whether you are working in the doping center, your results can be believed by your accused people or not. Of course, nonsense. Because they have a lot of excuses. That's clear for you. So that's why here now is I measure here in the Katara dose. 0.1% TFA, methanol TFA, and our methanol deuterium 6H6 level. This one is not bad. This one is not bad. This one is not bad. You can detect. Then, long time ago, TFA used TFA for acidic condition used for the alcohol. Then, why we have to use TFA instead of this one? Extraction, if you are not doing profiling technique, sometimes you have to consider selectivity. Selectivity. Now I'm interested in this compound. In the extraction level, if you have a best product, I extract the only this one is best, right? Because I suppress. So that's why they use TFA. But yield, of course, yield is important, selectivity is important. But our case, profiling technique, selectivity is opposite. We have to do unselectivity, unselective method. That is the point. Then now, yesterday I already told, I already explained to you. There is no single extraction method or solvent method to cover everything. Then automatically, naturally, you will think about why not? We can use all the solvents continuously. That was well. For example, now I extract methanol, water, hexane, chlorofluor, whatever. If you do this one, I combine this one, then you can have a more number of metabolites. Regardless of working time, is it useful? So that's why we did the multi-solvent extraction, so-called. We did some 10 years ago, comprehensive extraction, continuous extraction of plant material with a mixture of solvent for increasing polarity. For example, here, now I put this plant powder instead of extraction with one time, I fill with an empty HPH column. And then I start with hexane, and then acetone, and then acetone to metal. Then you can find this kind of. It takes a time, of course, but it can cover diverse metabolism. Then the question is, now you have a hexane from water. Which one must be the first to come? Hexane or water? One.
First order to be added to the picture.
But water can be added to the mixture. Yesterday, hexane is right. Then why is yesterday I told you extractability is competing with the matrix. If you added the water, then it's already most of the compounds is dissociated from the matrix. It's a blocking. There is a blocking. What you cannot get the selectivity. If you do hexane, okay, then epidermis extraction coming out. The other one. So when you want to mix the solvent, always starting from low polar solvent. That's the point. Then this one, of course, we have a limitation of the number of experiments. 1,000 sample we cannot do because one experiment takes several hours. But when it's good, now we have this method. Methodology I developed, for example, when you can apply. Do you understand my question? So now you have a technique, you learned it now. When you can apply? I give a few minutes, a few seconds. Think about. Always learning technique is also difficult, but learning technique is just short time. But where to apply for the, let's say, in the beginning, as I mentioned, to answer your scientific question, where can we apply this technique? Are you activities? Yeah. For example, now we have a unknown plant. You don't know, like yesterday, you case Alithia, you mentioned, right? You have a plant material. According to reference, because you selected the plant, unknown plants, right? There is a less metabolites are reported. Then in that case, if you use only one extraction, so probably you will lose some transportation. In that case, for the extensive work, probably you can start. But then you can do metabolic profiling. For example, all these structure, you have a like yesterday is anti-inflammatory data. You can correlate data. Which signal probably related to activity and experience. What's the advantage of this one? As he mentioned yesterday, but also he mentioned I have a lack of number of samples, right? Maybe I have only 45 samples. I have only 10 samples new species. 10 samples you measure actions like this one. Activity 10. Correlate. It's a little bit is problem because at least you need a certain number of experiments to correlation for the statistical significance. In that case, one sample produce or not extent, then at least you can increase. If you are talking about activity correlation, this is also. Do you understand my question? Yeah. When I suggest the protocol or the methodology, please think about your problem, how to apply. Now here, like this one, empty no column, one from you filled it, and then we started with the pump. So like the average is pump, we collect it here. But we never used for the real metabolomics before because it takes time. And we did some activity correlation. Yes, it's a correlation with some anti-inflammatory activity. Sorry, anti-microbial anti-inflammatory. Now plants more or less this one. The best solvent, the optimum solvent, I don't know what of this is. You can start it, but it's not perfect. You have to keep over. Once more, I want to remind you once more. If you find no difference, it's not science. It's very difficult. No difference to prove it is very difficult. To prove different is very easy. One time measurement, one experiment, and you found the difference is different. But one experiment, you found the same, it cannot be same. That is very important. Also, now Anithya, for your cases, you are doing some applying to some certain family species, right? Your question is, what is the unique metabolites of each species? This is a natural question. But in the other way around, if you find what's the common metabolites through the whole family, also it's interesting, that is really difficult. Now you have family, Babaceae family, Leguminosae family. Each species, or Pygium sativum, or Glacian next. What is the unique metabolite of Glacian next and Pygium sativum? You compare all these signal is only in the Glacian next, you find no problem. But what's the common metabolite to the whole species? Then is the very yesterday I mentioned, then it can be the use for the chemotaxonomy. It can be contributed lately to the chemotaxonomy. It can be the marker for this family. You can raise maybe someone is against might be against the system. Microbiome. Microbiome. So now it's of course not many people here are interested in micro. But some people are doing plant microbiome interaction. Let's talk about the microbiome interaction. Here, solid culture. For example, there are two kinds of culture: liquid culture and solid culture. The solid culture, when you do solid culture, Then how to do handling this one? The agar, right? What you have to be careful of. You can treat it agar plate as your plant extract, right? What's that?
Do I?
No, no, solid state you cannot take out one is altogether is like a plant. We cannot separate microbes. What is the point? Agar. Agar, it's not contamination, it's like a media cases. When you add in agar, same thing, this one, how to remove the agar? Of course, some people say, oh, if I extract the acid or non-polar solvent, then probably only leach the metabolite, we can detect it. But the problem is, agar is always. When you extract the water, agar is there. When you extract the acid, agar still leach you. Of course, in animal cases, in mass spectrum, probably agar is not very well ionized, but still it's a problem with the column chromatography. Animal cases, agar signal is very big. So there's an issue how to remove the solid culture. But liquid culture, what is the problem with liquid culture? Now is the liquid culture. You are growing microbes in the liquid, under the liquid. It's a media, right? Now it's a cell mass. You filter the cell mass. Then it's you crush it, you extract it. No problem. It's just same. Like you can treat as a solid material, right? But as I mentioned, metabolic footprinting is released secreted material in the media. Now it's a liquid material. How can you take out the metabolites, footprint metabolites? It's an excreted metabolites. Because there is a lot of media metabolites, sugars, or amino acid. Why? Because sometimes the worst scenario is some people using soya milk, right? For as a media, then soya milk is a mixture of plant material like plant. Still, I don't have any solution. Many people they are using after media, they add in ethyl because ethyl is most hollow compound to be not to be miscible with the water. Take out ethyl then ethyl fraction we can after dry we can analyze. That is that's how we focus. But what's the problem? Problem when I use media, microbial media, and then I add in ethyl two-phase is there. Two-phase, I take out ethyl I believe it's a footprinting. That's all. Metabolites excreted. It can be, but what is the problem?
Extraction.
That is a lead. Ethyl extraction means now it's not only the, of course some people are using the solid phase extraction like I see in color, you see in color, but still it's a problem. Now you have water wash it, methanol wash it, or methanol wash it what? Now, for example, streptomycin. It's a very water soluble compound. This one is still easy in the water fraction. What in the solid phase extraction? The first fraction together with the media called the amino acids, streptomycin is decreased. That is the so that's why some people using depending on this one. Like instead of SPE, we are not using often. You know which resin is quite commonly used in this microbiome technology? H20 resin. That is the HP resin. HP20 resin is the easiest one. It's like a filter type of the metabolite. You just pour it, take out water, and then methanol water or ethanol water or that is a little bit faster. And also SPE method is a very small one. Usually, if it's a big one, big size, it's very expensive. HP20 we can use it, but still, all of excreted metabolites is the issue how to detect. The sample preparation of before extraction, now sample preparation, then avoid unwanted chemical contaminants of liquid culture. That is very important. now it's not the issue of metabolomics, microbiome. One day you can find a lot of fungus and you have to throw it away. Plant tissue culture, even worse. Always they are contaminated. So that's why unwanted contaminant, you have to check very carefully and continue agitate bench cultures until simply for those comments, sedimentation. I explained you in the beginning yesterday the circadian rhythm and stress. So now you, in order to collect microbes, you stop agitate. Then it can be stress. The microbes they produce unusual metabolites. That's why very keeping this agitate very carefully and think of. And also, as I told you, some people said is that if your master, if you prepare, is very cold, and then temperature shock is possible. So that's why the same thing and spin out, and something like this one. And this will record better. This is the normal procedure of microbes. But depending on your target compounds, it differs. Keep in mind, first one is contamination, second one is to avoid any kind of stress. And here is the separation preparations, microbial culture, microbial. You can find it, but this kind is the same as plant material. Get detected. But careful, if you find some metabolites which might be in the media, like glycine or amino acid or sugar, keep in mind this one could be from your media. This is always final check. And simple preparation of microbiome culture is we grow the agar plant and here by the time what this kind of stage we did it. Yeah, we did it. So some signal is we can do this one. But always this one is agar culture, solid culture, keep in mind. Agar also to be detected in your final concentration. I don't know how much is ionization power in the mass spectrum. Agar also can contain your final extract. This is your more or less, yeah.
Sure. But in those cases, when you use all well below to constitute like 1% of any company, to see how stable those inside mind protein levels medium as other.
So that's a very good question. First one is when you do microbiome culture, plant cell culture, you have to make a list. Define the media. Define the media. Now you know which one is in the media. So that's why that one is not from your that is okay. Second one is yeah. If you are using non-defined media, like sometimes they put the soya meal, this is the worst scenario. Then please ask your colleague who is growing the center. Is it possible to use defined media? Defined media. And if not possible, I want to use the soya bean. You have to check it which kind of metabolites from soya bean. Like as I mentioned, glycerine, hydrogen, or some sugar. And keep in mind, those kind of compounds also can be degraded. The isoflavonoid in the microbes, they are biotransformed. That is the issue. But first scenario is the first checking point is you have to have a list of the media list. This is but now another one as I mentioned. So that's why the first day course is very important. But is if you find cholesterol, for example, ergosterol from plant tissue, probably it's from the contamination of the compound. That kind of information is needed. And also now is the issue when you are doing plant microbiome interaction, when you are doing Mozart, minus case is no problem because they are not self-replicating. When you extract the virus infected plant material, all the detected metabolites probably belong to plants, no problem. But if you do bacterial infected plants for fungi infected plant, you extracted the metabolites and you found some metabolites. Those metabolites, probably some percentage of the metabolites belongs to fungus. How can you separate? No, there is no way. So that's why after identification, you can give a label. What is a plausible label? You cannot. So keep in mind when you are doing plant microbiome interaction, when you do extraction material, when you do extracted metabolites, define, identify the metabolites, many of them is from plants, those plants, or microbes, or fungi. Based on that way you have to distinguish. Mammalian metabolomy, actually, all through the metabolomy, human metabolites, so-called metabolomics, is the most successful story because drug diagnosis. So you think so genetic person is started around 2010. There is many cases it's a successful story, and also research plant is more in human metabolism. Plant cases nowadays, plant now is more and more mass spectral, is often more often used than animal because it's more metabolism coming out, and plants and microbes they have more secondary metabolites, but still is in human metabolites. Their number is completely different, 1,000 to 2,000 sample. If it takes half an hour or 1 hour, it's impossible. So that's why animal is only a few minutes. So still, is animal is the most preferable. And so many protocol in human metabolites, biofluid, is targeted on the animal metabolism. But now, not animal is not enough as is supplement to use. Here, sample preparation for biological fluids. Plant cases, except for folium cell, most cases leaf, root, or flower, they are the same finished strategies. But biofluid cases is already filtered by human. So depending on the fluid, you have to use different types of fluid. The easiest one is what's that? Urine, because it's already liquid, and then blood plasma and serum. What's the problem with this sample? Protein. Yeah? Protein case. How to remove the protein properly? This is very important. And CSF, what's the issue? Huh? Exposition. Just this is correct. Once, as I mentioned, once we collect it, perfect method because it's a liquid, liquid, and it's directly injected into the even CSF. You don't need HPLC. Direct infusion method is possible. But the problem is you need to collaborate with the hospital and you need an medical issue. And this is the worst example which I have ever handled. What's the problem? Huh? Regardless of smell. What's the problem? Species, think about this. Species, nowadays, trans-species is very important. But you are different species because of God microflora. Species case is now urine. What's the state? Liquid, right? It's a liquid. Liquid. Feces, is it liquid? Is it solid? It depends sometimes. And is it gas? All three states are mixed. Smelly, gas, and I don't want to explain. And probably you saw this morning solid material and liquid material. There is no method to do 1-7. And another issue. If you have a human physics, is it only human metabolites? No. God microflora. And you ate today salad, plants, all mixed. That's why when you do urine analysis of blood, you distinguish very easy. So when you do component analysis, clustering is very easy. Like health the patient or the control. The control one, the patient one, then they are very well separate. This is always is a lot of variation comes up because of course we are controlling. Yeah, if we have a volunteer, every day you are eating and you don't smoke, you should not drink a coffee. Of course you control, but still still so a lot of variation, which means difficult. Which means for our metabolism, it's quite challenging. One is many people watch to do basis because of more information. But I don't know. Preparation is relatively simple. let's study sample, urine sample, urine sample. Now it's a urine sample. Urine sample is not only human urine. Sometimes you are using rat urine or mouse urine, or sometimes some people are using monkey urine because it's ethically you are not killing the animals. Good. Urine sample, urine should be collected under refrigerated condition. This one is very expensive. Now it's human, of course, you cannot put the human in the refrigerator. But when you collect the mouse, rat, then there is a refrigerator. It's around the cost. It's around 40,000 euro. Then it's a kind of a mouse toilet. So it's here, and then under the bottom is a temperature control. You collect urine. If you want to do, you can discuss with the medical doctor. Okay? And now add some amount of sodium azide. Sodium azide means NaN3. Why we have to use it? But antibiotic, there are thousands of antibiotics. Why we have to use the sodium azide? Sodium azide means Na, yeah, sodium N3 azide. Why we have to use sodium azide? Because if you have, there are many variations, I would suggest that yeah, you can use this. But sodium azide is the antibiotic, antibacterial.
Why?
Why? Why I have selected? Because usually I'm using NMR spectroscopy. Yeah? Sodium azide. Please look at sodium NaN3. There is no proton, so that there's no proton. Even you add it or not, you don't have to worry about the outcome of NMR spectrum. And also, I use the buffer. The buffer here. Sodium azide used for collection using refrigerated metabolic flex, as I mentioned. It's around like $40,000, $72,000. And for animal analysis, flow probe, centrifugal, 96 per plate, and I use buffer. The buffer here. Why I have to use a buffer? Because to avoid the chemical shift variation, I use sodium phosphate buffer, the NaH2PO4. I use my protocol KH2PO4. It's more or less you can replace. Why I use sodium phosphate buffer instead of other tris buffer or all other buffers available, right? Because also contamination. If you are using tris buffer, tris signal is the big one is coming out. But sodium phosphate buffer NaH2PO4, there is H, right? This H is replacing with the water. If you suppress the water, you can suppress the water. So that's why in NMR spectroscopy analysis, metabolomics for the urine, usually you have only two choices, sodium phosphate or potassium phosphate. You cannot use this. So that's it. You don't have to remember this one because I released this one. You can follow, but you have to understand each step. Now, this one, this kind of metabolites, compared to plant metabolites, there are only a few metabolites. Amino acid, sugar, but sugar you should not detect it because then you are diabetes, right? Urine should not have any sugar. If you have a sugar, then you are diabetic. Sugar, maybe you can use your urine to NMR, or whether you can diagnose whether you are diabetic or not.
Yeah.
It's very easy. And the second one is, I go to when you handle the biofluid, what it our most interfering metabolic group, the chemical group is protein. But urine, ideally should not have a protein. If you have a protein, you have a hidden malfunction, right? That's why urine is the easiest, and also metabolomic. They start with metabolomic. Clinical study started from the urine, and also urine doesn't matter. Doesn't matter. You collected 1 liter, 2 liter, anyway, your organism is still alive for human beings. Now, many people, urine has a very limited metabolism, so that's why they move anytime. Plasma and serum. What's the difference between plasma and serum? Here, I mentioned here, sometimes, I know you already know, But to make sure, plasma is liquid component of blood where coagulation has been prevented. Serum after coagulation. After coagulation, if you take the blood in the beginning, it was liquid, right? After keeping some time, then all protein coagulate, then it's coming out. That's the serum. But plasma cases before coagulation. Before coagulation. And serum sample preparation require about 30 minutes because it's and waiting that protein can be transfused and then analyzed. And during coagulation, blood cell consume blood glucose and something like this one. There are many kinds of issues. You can compare it, which one is easier. And then here, now blood metabolomics like serum and plasma. NMR is still most mature tool. Now here, SMS is around 900 papers reported, and NMR cases still is several thousand, 1,300, and GCMS 816. But these cases, GCMS usually in blood metabolomics is very limited because they cannot detect properly secondary metabolites. But in the blood sample or even urine sample, they are more or less a similar number as SMS. Why? Because human metabolites mainly is primary metabolites. It's really small molecule. Like maximum is glucose. We don't have a starch except for your feces. So amino acid, organic acid, or sugars, even they need the derivatization, still it's very nice. And also one of the advantages of GCMS compared to LCMS, what is the advantage? They are using often EI, electron impact spectrum, for several decades, least, or RNA, they accumulate all the data. A lot of metabolites already there. You upload it there, automatically comes out. The accuracy is not comparable. It's uncomparable to the HCMS. So once, always, I have some sample. Yeah, I have some sample. There are two choices: NMR, also the HCMS, and GCMS. GCMS. If I put no problem for the sample preparation, I can follow GCMS. If it's not secondary. Why? Because database issue is already solved. But if it's a secondary, like feces cases, then we cannot use GCMS because a lot of metabolites from microorganisms or GCMS plants are included. Yeah. So practical aspect of blood sample now is experimental design for sample preparation and metabolic extraction. So HMS, deproteinization, and then the filtration and centrifugation directly measured. This is clear. Yeah? This is clear. But deproteinization, what's the most common method? Deprotein? Which solvent? Acetonitrile. Many people use it, they add in acetonitrile. Then protein is practically after centrifugation. This is good. Some people are using methanol. You can use both. Yeah? Either acetonitrile and methanol. That is the same. Or then you have a question, why we are not using this deproteination in plants? Because we need it. Because when you are, so that's why always the suggestion is when you are doing water extract plants, now is you have a plant material. Now I want to extract water. And this water extract, you have to consider about the deproteinization because water can extract a lot of water. So that's why I prefer when you are doing plant metabolomic, organism 50% methanol or 100% methanol, it's already fresh precipitated protein. You don't need a special step. What is already including the deproteinization step. But in HMS, only one step. GCMS cases, deproteinization, say, after the methoxymation, I will explain later. This one is if the compound is a ketone group, if you have a ketone group, this ketone is blocked for not to go further. Then TMS derivatization and centrifugation is rejected. NMR, simple dilution, dilution, and then deproteination and centrifugation. And it takes only few minutes. So this is a similar, always deproteination, you need it. You need it. And now, maybe I forgot. When you do urine analysis, yeah, you can inject directly urine to the SMS. It's no problem. Because it's already filtered. Maybe some membrane filter you can inject it. But in animal cases, if you have a urine, do I have to reconstitute with deuterium solvent or not? Now you urine, right? This one is normal solvent, like H2O. But animal, we have to use D2O. How can you solve this problem?
Utilization.
Huh?
Utilization.
Yeah, right, dry. What equals to D2O? But then there is no method of animal compared to the mass spectrum. Evaporation and reconstitute the D2O, then it takes a time or during this, then probably you will lose a lot of compounds.
Freshly water.
So freshwater signal is possible about 100% of water. So that's why nowadays many people think we have to use deuterium solvent, but it's not true. We can add how much if it's to get percentage for the law.
You can use external reference if you want. So you don't need to put G2O or any different solvent. You just put a capillary inside and you take the urine in that.
But there is a little bit shimming issue.
Yeah,
Because
that problem.
shimming means you need a certain amount of deuterium solvent to make a peak shot. So that's why official protocol is if you take out the urine and you add it 40% or 30% or sometimes 50 to 30% D2O dilute. Then D2O is there, you measure. You don't have to freeze trial or you don't have to live directly measure. This is an issue. But blood sample also same. So here there is no evaporation phase. There's no evaporation after dilution. Dilution means we don't need to we don't need to solvent, and then deproteination and then and plasma cases. Obtain blood in here plasma in transport plasma containing leukocyte and platelets in the propylene buffer and aspirate plasma from the platelets. So you can find out all this one now. Most important one is anticoagulant you add it. Yeah, because plasma different from serum. This anticoagulant is EDTA or unstable ascorbic acid or heparin cases, but EDTA also animal serum. And heparin, even though it's a protein, if you add in too much heparin, signal protein comes out, heparin signal is there. So that's why the plasma is more difficult to be handled than serum cases. But sometimes we need it because there is more information, protein.
To show its final marks as we are now see simplification is like a standard protocol. But my concern is about when you use simplification, in this case, protein is not complex nor costly.
Good master. So that's why it's in short time. If you keep the long time process sample, they are containing the compounds. So which kind of internal standard are you using?
Well, for blood,
No, I mean for any kind, like a TSP?
TSP, but for blood,
Yeah.
the DSS.
Yeah. TSS also say TSS or TSP is we are using animal. If you know the animal, we are using auto calibration. Yeah, calibration or some concentration. You are using certain amount of TSS or TSP.
TSP.
But in blood sample, you add it. Yes, even TSS also say, and TSP is the same protein. Yeah, protein captured. Or you cannot see those internal standard. So then in that case, it's not only compound, as you mentioned, it's like a conjugated oil capture. To avoid this, you have to use a fresh sample and internal standard, external internal standard, or another internal standard. You have to use this is a protein. It's not only signal protein, and also it can conjugate or interact with other small molecule. You cannot detect. For example, protein is a lot of NH and COH there, right? Then its compound is tightly bound there. If I bound to the protein, this one cannot be detected in animal spectrum, or it's included broad spectrum. So this is your point. So that's why two reasons to remove protein, yeah, signal protein in mass spectrum multi-charged material. The second one is to conjugate, to interact with the molecule. For that reason, to have. Any question? So animal spectrum of plasma. Please look at this one. Now we started to protein here, but after proper separation, still is quite nice. But if your sample contains high amount of protein, you signal is comes up. And sample preference for serum and cerebral spinal fluid. Serum, is anticoagulant, that is protein more or less is removed. And for serum blood, it's collected to propellant tube first. And then serum should be carefully aspirated to avoid. And then like this one. Yeah, there's not much difficult compared to plasma simplifier of this. But here, propellant tube. Plasma sample, I also mentioned propellant tube. Why I have to use propellant tube, not glass tube? Because if you are using glass tube, there is protein or metabolized bound there. Blood sample propellant, like a plastic tube, be better. Usually, you don't want to use a plastic tube, right? Propellant tube. But in that case, better to use propellant tube for the blood sample. And serum. Sorry, cerebral spinal fluid. As I mentioned, simple, like a centrifuge, you can directly measure. So one of the simplest one. But serum, what kind of compounds are most common in serum? Sorry, the cerebral spinal fluid. I mentioned the capacity. Nucleic acid, type of the compounds. There are many nucleic acid compounds adding guanine, cytosine, thymine, or if they are derivatives. That's why, because it's a neurotransmitter cases. Those cases, neurotransmitter is very full information. What kind of method is best for this one? Many people are using CE as capillary electrophoresis. Usually our natural product does not have a charge, but adenine, guanine, because of that is a charged material, capillary electrophoresis with mass spectrum. Some many people specifically use for the cerebral spinal fluid. But of course, you can use LCMS. Or even sometimes, because it's a cerebral spinal fluid, very small amount. If you dilute the LC, you will lose a lot of compounds. Some people are using after purification, after the centrifuge, you can do directly infusion. Without HPLC, then directly LCMS, because it's a very small amount. Then we don't have a problem with ion suppression. Question? Is it clear? Yeah? Plants, microbes. You don't have to remember, but at least what we should be careful. This is very important. And now, yeah.
Yes, I don't know if it's common to work with saliva example. Could you talk a little bit about it?
Saliva, I did it before because my former boss, Robert Conte, he wants to do it. Yo, please try with the saliva. Saliva means spit, yeah? Spit. But it's not like a urine, right? Saliva means enzyme is there, right? That's why precipitate with the acetylene supernate to be that. no proxy.
Straightforward.
Of course, saliva is also is a very individual variation. Yeah.
Yeah. Both.
Coffee, smoke, whatever, chewing gum, yeah, so that's why if you want to do some research with the saliva, yeah, saliva, don't collect the sample from your friend. Yeah. Please go, you need a professional panel. Saliva is because as long as it's a liquid, and also collection is very easy. Yeah. Saliva. And other issue, hair samples, hair also, when it's using hair sample, when they are doping test, like cocaine, basically in this case. But what's the issue? We have to be careful. No, you don't. But if you extract, you can either understand. What's the issue of this one? Now, depending on the sample, you don't have to remember everything. You have to remember what we should be careful. Hair sample or some this sample. What? First, your target metabolite. You want actually that there's no target. Metabolites which you want to detect is a very small amount. Okay, how much is it? Of course, we don't have it, but there is very big common targets. That's why analytical accuracy or sensitivity is a very important issue. Second one, usually not the mathematics is your polysaccharide or something, but this one is collagen protein. This collagen is more power to bind your metabolites. That's why I mentioned to break this one is a very issue. Sometimes you are using acid, like acid cases, or long times ago, supercritical fluid chromatography they used. So that's why extraction protocol is not only on the solubility, it's a dissociation. First, this one is a very important issue. Others, any samples which you are interested in? Soil, right? Nowadays, soil. When you are doing soil analysis, the soil is the most unknown mysterious field. Many people want to do. What's the problem when you are doing soil? Think about this one. Now your boss asks you to do the soil analysis. Because plant microbiome or loop exchange interaction, we need the soil analysis. What is the point?
Sorry, I was writing and didn't get
The soil, when you are doing soil chemistry, soil extraction, what is the point we should be careful of? One word, homogenation. Do you understand what I mean? On the top of the soil, not about the leaves or whatever, or even the smoking bar there. But depending on the depth, soil is different. And also, soil is not only pure soil, microorganisms, or even plant powders there. So homogenation is very important. Seeding, of course, plant, I told you, at the dry, the seeding is efficient. Five powder, we can extract it. Seeding and depth and where to get it, what water content. It's very important. So that's why when you mean the soil analysis, always you mean fumigation. Sometimes word fumigation. Chemically, still I am confused. What is the exactly chemical fumigation? It's very different. So homogenation, right? Homogenation is the issue for the soil. Any others? Any others? Example, are you interested? Meat. Meat, same as a blood because it's a protein cases. Meat cases, meat also same. When you are doing meat analysis, metabolomics, what you are interested probably, yeah, it's like antibiotics, or antibiotic, or pesticide, insecticide, or those things. Very common. Same as a hair analysis, very minor. In that case, usually you may do the targeted analysis. I want to detect the western and in that case, instead of the Q-top, you use well, TQ, triple quad would be nice for the quantitation case. Like a plant hormone cases, maybe I can explain later. There are many methods. QSOC is most common metabolic profiling method or instrument. Well, even if you have more money, obviously you can use it. But if you have a targeted analysis, plant hormone, instead of a coverage, I need a sensitivity. The sensitivity in that case, TQ also can be used, even better. Targeted. Difficult. So cerebral spinal fluid. Let's look at this one. Beautiful and clean and weaker analysis. So already you can smell, right? Extraction. Uh, frozen fishes. Frozen fishes, of course, it should be frozen, otherwise you cannot handle it. And extracted with the PSD, yeah, phosphate saline buffer. Phosphate saline buffer. And then, phosphate saline buffer is including this one. But then sometimes when you do protocol, when you follow the protocol, this protocol sometimes you don't understand. Why? Because the protocol developer didn't test everything. They just used this one. They reported everyone is follow, like a roaming to the cliff. But this one of the person they developed this method, this for PSP buffer. But when I use other HTTP buffer, it was okay. But official protocol is why I have to use this protocol. Maybe you can compare with the previous literature in fishes analysis. I used also when I doing follow this. Although when I checked the KH report, it was not bad, but I used this. And it got me my supernatant F% deviation. What was the problem? This protocol, we gave a gas phase. We gave a solid phase. Then we have a part of which is chemical information. But then now it's a leftover. Yeah, leftover. Probably this leftover we can do solid state animal or vegetable mass animal. That is your question. Some people I think already did it. Okay, liquid supernatant I use SNS or animal. And then the dried material, the leftover mark we use with the solid state animal. Because it's mostly is saccharide. And pickle, what is that? Pickle supernatant. Pickle supernatant here. Look at this one. Message is, what is the main component? Plants is a secondary primary metabolite, so blood sample is more or less primary, and this is sure if this is sample, my experience, my experience, short chain fatty acid is the most common. Short chain fatty acid means butyric acid, propionic acid. Those kind of short chain fatty acid here is a very unique, or even acetic acid. Acetic acid or formic acid, you can detect it. But because those acids are from God micro, God micro. So that's why some people who are even including me, okay, if I want to target this short chain fatty acid after animal, probably those samples I can do gastropatho, they can do binary short chain fatty acid. Instead of animal HMS, maybe you can use a helic column, but normally C18 column, there is not much retention time always in the beginning. Instead, after NMR, I prefer to do with the HMS because main product from microbes short chain acids.
But the microbe includes in that oxidation. Then you have a small.
Yeah. That's a good one. But in animal cases, I can roughly identify the major short chain deviation for oxidative compound. For those, I would like to use just power. Because, sorry,
Milk. Yes.
milk.
I can use the same concern that I have with
What is that? Milk.
milk. Now milk from brown.
Milk, you mean milk. It's milk, yeah.
Yeah.
Have you ever tried with the animal with the milk sample?
No.
No. It's a turbid sample, like a honey sample. It's a whole. That is, you have to decide. Now, okay, milk is very nice. Sometimes milk, why? Because I don't trust the farmer because they put the antibiotic there. Yeah? Now you have a milk sample. What to do? What's your plan? Now you have a milk metabolism. Yeah? Cow milk or oat milk or which milk? Sheep milk. Yeah? Now, first, I want to compare sheep milk and cow milk. How much they are different? It's interesting, right? Of course, I guess. Yeah, then how to extract? Would you explain your plan? Yeah.
All the steps pretty much the same preparation, centrifugation, protein precipitation, dilution, everything you can use.
Then what's your name? Yes.
My name is Isabel.
Isabel. Then now you have a milk. So before planning, what's the first step?
Great.
Yeah? Drink. Then you define correct. Yeah? Right. Instead of dry, pray to your God. That's it. First one is now, as I think he already mentioned, what is the metabolized in what is the chemicals in milk? What is are they? Protein, lipid, water, sugars, sweet, those things. Now, if you have a perfect method, I use it. Yeah, I use it, but it's impossible. Right? It's impossible. First, if I go you, I will divide it. Are you interested in protein? But I'm a metabolomist. I'm not interested in protein. Okay. Then how to remove the protein? That's the issue, right? Then I never use, but first I will centrifuge. Yeah. Then this will take up. But before that, maybe I can add some organism like a blood sample. Like a blood sample, then you can take a supponate. Right? You can take a supponate. Then protein, white one, separated, maybe cheese, right? Some cheese or butter, take out this supponate. Yep, done.
Can I do an acidification of the
Sorry?
acidification?
That is possible. But acidification, when you do the acidification, if the samples contains a protein, it will be problem because because of the protein. After protein, you have a supernatant. Yeah. Then this supernatant contains of what? Lipid and some antibiotics or some from grass. Those one. Now you have to decide if you interested in lipid. Yeah? Lipid, or I'm interested in four. You can divide half of them. I want to do fatty acid analysis. Half of them I go to the LCMS to do analysis. If it's something wrong, then I will. So centrifuge, deproteination, and then gas chromatography, or NMR, that's the first. Based on what you learned here, you already make a plan. Then now don't forget, before starting planning strategy, this one you have to think about. You have to first step is what is the step that I mentioned? You have to know you have to guess which kind of metabolites are there, protein, lipid, whatever. Based on that one, you can divide. Yeah.
When you separate the protein and you want to analyze the amino acids in the sample, is it a problem?
No, because when you do precipitate, of course, there is some co-precipitate is possible. But if you keep long time, it's co-precipitate is possible. But if you take down the protein, amino acid still is a super. As we see in the animal spectrum for amino acid, protein, chemical character are different.
But if you're looking for a hairstyle in the milk,
Yeah.
Maybe when we're first.
So that's why that is always is a tricky cases. So that's why she suggested probably we can add some acid, whatever, and we can degrade it all the compounds. But always first try with the simple method. Yeah, pesticide, herbicide, probably there is, there is. But I would prefer, after centrifugation, I immediately go to the animal because animal is not destructive method. After animal, you can measure it again. Right? After animal, I have a look what kind of compound it is, the circulator. If we found some, then you can make a second plant.
Professor Shaw, in case of animals, what is your suggestion to
Animal,
animal? I mean, like stage
sorry,
small birds or eggs from birds. What do you think?
egg. Okay. Shall we start with my experience? Do you know viper? Snake. Viper. My colleague Netherlands, he collected all the viper, king cobra, black mamba, barracuda, and he take out the sample. He take out the sample, he collect the sample. You know, to measure metabolism. Actually, viper, and also he's provided the spider venom, spider venom, snake venom, the scorpion venom cases. Yeah. Now all these samples first start this one. Snake venom and spider venom is completely different. Then you have to look into the literature. Snake venom, what's the toxin? Protein. Protein cases. So that's why now, yeah, if you do a snake venom metabolomic, actually metabolomic doesn't make any sense. If you are interested, regardless of protein, what kind of metabolites are there, then it's interesting. But spider-venom is a small compound, small molecule. Then the snake, sorry, the spider-venom, you can treat it like a CSF or others you can treat. But snake venom case interests me. I just measured without any precipitation. I measured animal spectrum. Do you know what I found? Black mamba, king cobra, whatever, and tiny snake. Of course, protein is there, but protein I cannot distinguish. What kind of compound is there? Citric acid, lemon. I thought that viper is a vegetarian, yeah, but actually it's not true. There is a story started. Why? Why venom? Well, snake venom. Snake. They studied the citric acid because citric acid natural anticoagulant. So when they bite it, blood should be flow. So that's why citric acid is. But your case, egg case. Now egg, yeah.
But I need from birds.
Birds.
Birds like sedation or
Birds or
bird insects.
insects. Yeah. Insect cases, yeah, many people think, okay, head, yeah, and then here should be different. If you can separate, of course you can separate, but careful. Now you have to think about the accuracy of analytical tool. If you take out all the head, then probably there are more toxins there. But when I did it, I was not very successful. So instead of this one, just grind these cases. What's the main matrix in insect? Keratin. It's like hair. It's like hair, so you can treat like a hair cases. So always please think about what kind of metabolites are there. Then it's a keratin cases, you inject it, you extract it. And also, like in traditional medicine, do you know centipede? Insect which has 100 legs. That's one is being used quite often here. Rheumatism. They boiled with the chicken soup and they eat it. Believe or not, they are still being used. Yeah, centipede. When I did it, extraction with this one, of course, it's a protein cases. Then protein, how to remove the protein from the extract is very important. The protein case. Matrix is a protein, extract the protein, how to handle it. And sorry, one more. That if you have a mold, do you know mold? It's like a butterfly, yeah, butterfly. Then there is a powder. Yeah, you're interested in powder. Okay, then now it's a powder, there must be different compounds, right? Surface. Now, your powder. Do you have any suggested sample preparation step? Even analytical chemistry is possible. There are several ways I never use several ways I can suggest. This mode sample, probably you can go to the mass department, Manito mass. Then they can scan this metabolite, which kind of metabolites are there. This is of course possible. But if you don't have a nice relationship rapport with the other group in the mass, then what's the best way? You can look for the old method. It was being used for the surface chemistry of plants, the vitamins, very old time. Of course, if you have a nice relationship or if you have a multi-top imaging technique, very nice. If you don't have it, in that case, I would suggest long time ago when you want to do surface chemistry, cellophane tape, yeah, cellophane tape, you take out this one here and you extract it with some organic solvent. That is also possible. But always methodology depending on your situation. Of course, yeah, best method can yield the best result. That's I clear. But your situation never be perfect. So that's why always check it out which kind of. And others, yeah.
It's kind of probably a new way for to analyze the metabolomics of raw fluids. Can I use it from the first moment that experiment spread? Can I use sequencers? Yeah.
Oh, yeah.
But not on pesticides. You see, the letters
Yeah.
is good for the
Yeah.
plant
Yeah.
lives too. Yeah.
Like now is a lesson. It's a little bit different story. One day I got some question. Who is using the wine, the grape? Yeah, she's doing grape residue, for example, after making or maybe translate. You want to do fruit metabolomics. Fruit metabolomics. Yeah, want to do fruit metabolomics, apple or pineapple. What is the problem? When you do fruit metabolomics, please expect what kind of problem it is. Now you want to do like orange, yeah, orange fruit, or grape, not leaf fruit itself. I want to compare orange fruit, yeah, depending on the region, yeah, Brazil or Florida, for instance, yeah. When you measure, directly you measure orange, you peel out, you take out, you inject in LCMS or GCMS, NMR. What do you expect? What can you be expected to come up with? You said only sugar, because nowadays cultivated one is very sweet. You can detect only sucrose. So because now it's dynamic range. You know, dynamic range means if you are interested in the ant, insect on the top of the Everest mountain, when you do telescope, you can see only mountain. But if you are interested in ant, how can you do? That's the dynamic range. Animal is rather, it's okay. What? 100% is fine. LCM has rather narrow range, right? 1 to 10%. If it's more than this one, always flat of this one. Then also ion suppression problem. Now, she wants to do orange metabolism, Florida orange, and she extracted normal solvent, according to my suggestion, extracted. And she only detect the sugar, sucrose. Then which means her result, even though she claimed that I'm growing, is only sugar. It's like a sweetness taste. But she wants to do, because sweetness taste, we don't have to do. There is a lot of nice method to test the sweetness. Bricks method, right? Method. You don't have to do. In that case, what can I do? as you suggested, we can, in that case, we have to use solid phase extraction. For example, of course, our metabolism should cover everything. Now, when I checked it with animal or SMS, nutrition, only I can detect only sucrose, which is not interesting. In that case, I can sacrifice, okay, or I can add one more step with the SPE, then extract. After extraction, we wash with the water, then all sugar coming out, and then the other polyphenol. Right? You can detect. This one is also applicable to marine organism. When you do marine organism usually kind of metabolize is very high because they don't want to be wet. The deep lipid is here. But when you do marine organism extract organic solvent, all the lipid comes out. Are you interested? Of course, it can be interesting in the beginning, but after taking out deep fat, deep fat is a very important step for the marine organisms. Yesterday I shouted a lot. Today I had a pain on the voice. But I forgot today. I shouted again. So I know now my voice. And do you understand? So now it's kind of exercise. So what you learn is not protocol for me. What you learn is how to make you by yourself. That's it. And of course, when you make a statement, you should not decide by yourself. Always you have to communicate or discuss with your colleague, friend, or supervisor. Then, for this discussion, each step you suggested, you have a reason. Once you have a protocol, you have to follow without thinking. This is other analytical platform. So here, sample preparation in GCMS. Sample preparation in GCMS. So now, yeah.
Before you start talking about this, I have another question.
Yeah.
When you have a sample that has different stages of maturation, what which do you choose?
This is a very good question. Modulation basis. Now, actually, I have a question to yours one and Alice one. Actually, it's a related one. Now you collect the plant for the chemotaxonomy, right? From the wild. The right? You collected some plants.
Yeah, I just grabbed from the herbarium.
Yeah, but anyway, they collected the plant, right? It's not. It was not grown. They were not grown in the greenhouse, but we collected the wild, and then you evaluate sample, right? Then you measured metabolomic. You said, oh, metabolic different. Okay, this species contains this one. This species contains this one, right? But my question is, actually, when you compare two species from herbarium, can you be sure it's the same age? No, right? Can you be sure same age or not? One of them is 10 years old. One of them 100 years old. Your metabolic difference in this case is not because of a genetic variation. It's because of age variation. Now I'm not very good looking. When I was young, they said I'm good looking. Yeah, depending on your age, it's a completely different story. Yeah, right. Then now our question is, and also another one. Even you believe, okay, you ask your colleague about you, would you collect the species more or less the same age, 10 years old? They can do, right? Then they can hide. But the problem is now they collected leaves from here. It's a young leaves. They collected from the bottom, yeah, from the bottom, then old leaves. Now you compare this one, developmental stage is completely different. Your metabolic difference is not because of a species effect, it's because of age or developmental stage effect. That should be very careful for the wild sample. I don't have any solution, but you have to. To solve this one, you have to collect more number of samples. There is only one solution. How cases? Now, I can grow two species in the greenhouse. Yeah, greenhouse. Now, how can I, now, of course, if I have money, time, I can do all stages, yeah, 1 year, 2 years, 3 years, any, or even upper leaf, lower leaf. This is possible. But I always have only one sample. Which stage is best? Younger leaves Of course, your risk specific. I don't have to wait. But it depends. For me, I cannot answer. Usually, when you are young, like the alkaloid produced plant material, the seedling level, they say there are more alkaloid because they protect from others. If you have older leaves, always organic acid, malic acid, citric acid is higher. But based on our common sense, I think in that case, what do you think? Probably full matured sample will be nice for the species effect. This one. But to solve this one, at least two stages should be compatible. And also, age is not only the plant age, and also important one is age, the developmental stage. In the same plant material, upper leaf, lower leaf, I did a lot of experiments. This one completely different. Yeah.
Sure, can you might like get upper leaves, medium leaves, and bottom leaves, different ages, and homogenize everything and
That's the solution.
go for it. For this
Then the question is, how can I trust? How can we trust your homogenization? Because most of this is not like this. Always is a burden of this one. If we collect it, or so of course, it's homogenization is the best option, optimum option for you. Alisa, do you understand your the technical issues? Is the answer to your question? Yeah. Analytical question is like coming out in the same one. So here, this one is the official protocol. You can follow this one. You collected the product, and then usually SMS, GCMS, they are using fresh sample. Now, when you do GCMS for the with the TMS derivatization, our target is sugar. The sugar target in metabolomics is rather absurd, but anyway, it's a sugar. In that case, GCMS, HMS, you added methanol chloroform, yeah, chloroform, and organic part, they throw it away. Because HMS cases, chlorophyll is always issued in the column contamination cases. After that, this methanol part is used. GCMS is also same. Although GCMS, they are doing with a volatile, but sugar is non-volatile after chemization. Of course, it's a volatile. Then take out the chlorophyll part, and then they are using this case. After that, TMS differentiation. This is a message. Of course, it's a very complex one. Message is, as I told you, the optimization of sample preparation, always you have to consider what kind of analytical technique are you using. So if you are GCMS, you have to follow this one. NMR cases, please suggest. GCMS, here, 360 microliter frozen sample, fresh sample, 60 milligram, which means it's around the dry weight is 6 milligram. And then competition of extract solvent, ABC. Here, polar international standard is added. And then here, here 2 milliliter is chloroform. Yeah. Here, sample and chloroform vortex, and here 400 microliter water, and take out this. This one is chloroform part. If you need. And SMS cases, so solvents, usually methanol, ethyl acetate, acetone, and equal ratio of water and organic solvent. Yeah? And once you decide it, you don't have to test other samples. Always follow the your protocol because it's already proven. What I mean, there are several protocols like this. And then extraction efficiency, chromatography behavior, extractor stability, ST5 and aqueous methanol. So formic acid. Why we are using 0.1% of formic acid? Ionization. Ionization cases. But some people believe formic acid was always we are using the chromatographic fluids. Yeah, in chromatographic fluid SMS, we are using formic acid. 0.1% is a very reversal solvent. But sometimes this 0.1% formic acid is not working very well. If you have a saponin rich sample, you cannot get successful result or something problem with the ionization, always is acid condition lower down. 0.01% of folic acid sometimes very working very well with the saline rich cells, but it's very rare case. This one is universal solution, but some compound here, some patient 50 you can find all this. And of course, I don't know how to explain all the analytical methods is reported. They are reported. The animal spectroscopy is a marine organism. Plant sample is my paper. It's a plant. Here you can find it. Usually, natural protocol in certain period around 2000, around 2010, there are many protocol papers. If you are interested, you can have a look at those papers. And amount of samples, now we have a several method. The amount of samples. How much we need? GCMS, 60 milligram per GP, then more or less 6 milligrams. But it depends. It really depends. More sometimes 20 milligrams, sometimes 10 milligrams. Yeah, but more or less this one. And LCMS is around 100 to 200 milligrams, which means how much is it? It's around 10 to 20 milligrams in dry weight, more or less equivalent. But this LCMS species, fresh weight is another problem. Is when you have a fresh sample, it's very difficult to weigh. Right? It's a well sample. A dry sample is much easier. But LCMS, GCMS, they don't care, so they are using this one. Animal cases around 100 till 150. Actually, it's not true because it's already exchanged. So if you are using cryo which you have here, is 10 to 30 milligrams more than that. Right? And the animal of urine, always animal 300 microliter urine plus here is solvent. And then animal feces, maybe is because we cannot weigh this kind of a superheat. And replicates, I think in the beginning on the first day, we talk about the replicates, you mentioned all replicates. Now, there are two kinds of replicates, technical replicates and biological. Ideally, technical replicates, you don't have to do. But LCMS cases, technical variation fiber, once you measure today, tomorrow is different. But animal cases, for me, one sample, one measurement. But LCMS cases, 2 or 3 times, GCMS also say, 2 or 3 times you need one sample, you have to, even you prepared all the sample, right? Today you measure, and after some time later, you have to measure once more. Once more, then you compare. It should be same, ideally. But sometimes it's not same, and it's a problem. So that's why in the animal metabolomics, we don't have a QC sample, quality control sample. Just one measurement, second measurement, third measurement, it's fine. But animal metabolomics, you are using QC, right? Quality control sample. Quality control sample means now you have a 10 kinds of sample, yeah? 10 kinds of sample. I mixed up together. To prepare a QC sample. Easiest way is then extract the several times. Then it's included in your final answer. This is a QC sample. QC sample means every time, of course, every time this QC sample should have the same result. If it's different, it's a mixing. So that's why to monitor technical variation, mass-based one, you need a QC sample. How to make a QC sample? Easiest way, if you have enough number of samples, all the samples you mix them together to prepare QC sample. Biological replicates is very important. Now, Alisa, you did it, the species, right? But you want to compare the species, two species you said is very different, but you cannot trust. You need a biological replicate. So one species, you have at least 3 samples, yeah, different age, whatever. Then this one is your species metabolic character. One measurement, as he mentioned, okay, yeah. Now is all of you are Brazilian. Yeah? But if I choose only this guy is a Brazilian, should look like this one. It doesn't make any sense, right? any kind of a scientific result is not point, it's the range. This range can be obtained by biological replication. Let's keep in mind. How many biological replications? If it's a non-controlled system, you need more. If it's a controlled system, you have a less. This is important. Technical variation is how much we can trust your technicals. So depending on the measurement, you can choose how many cases. Usually, biological replicate is much bigger than technical variation. Otherwise, you don't have any reason to use that technique. Right? So I cannot give a definite number how many biological replications needed, but I can say only at least 3 because it's for basic studies. And any questions? So shall we have some break and then I'll continue this. Any question? I think I'm very satisfied with your activity today. I didn't do this lecture by only myself. You did it already. You suggest the strategy, whatever. Particularly, thank you very much for you. Thank you very much for you. So I want to keep this way for the second of this session. So feel free. There's no one to push you to learn. Just to be open. Also, he mentioned yesterday, always discover to learn new technique. The barrier to learn new technique is not outside, in your inside. To break down barrier is very important. When I first learned animal-based metabology, my former boss, Robert Bortegi, asked me, would you measure plant extract in animal? Yeah? To prepare the sample to go to animal department, it takes 6 months. Why? It's not because I didn't have an animal. It's because I knew some of animal. Animal, I thought, in my opinion, is only pure compound structure elucidation. But if I'm measuring animal, one animal measurement is more than enough to make me crazy, drive me crazy. One extract, 30,000 or hundreds of compound extract, it doesn't make any sense to me. It's not worth it to me. So that's why I think it was my barrier. After breaking this one, so that's why you learn this one. Always learning is your interference in your inside. Okay, thank you very much. See you the next time.
Can you hear me, please?
Professor Lúcia Pinheiro Santos Pimenta. Professor Young, I would like to know more about your comment about the chemosystematic study. If I understand correctly, do you not approve of the use of plants collected in the field, but on those grow in a greenhouse, even if the biological replicates were modified? Another question I have is about the samples used in metabolomic analysis. In your presentation, you did not mention the use of plant extracts, only plant tissue. Can plant extracts be used in a metabolomic analysis? If so, how many milligrams should be used?
The first question is the chemosystemic, let's say chemotaxonomy. Yeah. Can we do chemotaxonomy from the wild plants? This is the first question. Is that correct? Right? Yeah. Okay, then let's do first with the first. Yeah, first thing first. Yeah, let's do with the first question. Ideally, if you want to do chemotaxonomy, like systematic analysis, you have to collect the seeds. It's like you can follow my paper in 2011, Alex species paper. What I did together with Argentinian people, they collected through all 10 years, they collected all the Alex species from all of the South America, Brazil, Argentina, Alex Paraguayensis, Paraguay, or some other places. They collect the seeds and they grow those plants in the greenhouse. And then they are analyzed. Even first generation is not enough because first generation still they have a legacy from the environment. So second generation, you have to use it. Yeah? This is ideal situation. This is ideal situation. Even when you collect the Lex paraguayensis, they collect, actually not me, my colleague, they collected one Lex paraguayensis from in 1990 from Paraguay. Elax paraguayensis from Brazil in 1991. Something like this one, same species, biological application. I collect the seeds and I grow in my garden. I harvest the sample. That was the ideal situation. But when you are doing, it's impossible because it's a 10-meter trees. How can I collect the seeds to grow? We can wait 10 years. I wouldn't say it's impossible. It's possible, but you need a more number of samples. More number of samples is not just the number of samples. You have to collect more vector sample, like a 1 year old, 10-year old, this leaf, this leaf. You collected everything, then you can find the common metabolites in this species. That one is can be compared to this one. So that's why certain number of replicates you need it. Is that correct? It's not impossible. Of course, no one can grow the plants, 10-meter tree in here, but at least a certain number of replicates you need. So that's why now Mateus yesterday he showed if you want to do but different story, it's not chemotaxonomy. He collected all the species under the same family, 10 species. But if they want to do correlated with the bioactivity, do I need the replication? No, you don't need the replication. Just I'm using plant material as a chemical resource. If there is a variation, I want to check whether it's reflected on the activity or not. So then in that case, number of plants is more important than replicators. But if you want to do the chemotaxonomy, I'm not interested in the activity. I'm interested in what's the genetic effect on this one. Then you have to remove environmental factor, whatever. You need the replications. Different story. So now you have a two aspect. You have a two aspect. Now chemotaxonomy, then you need a certain number of each species. But if you want to correlate the activity, you rather you have one replicate, but very diverse metabolites correlate to this one. This is important. Is the answer to your question?
Oh, I think
You
so.
I hope. And second question, what was the second question?
Uh,
Second question,
can plant extracts be used in metabolomic analysis?
can what?
Can plant extracts be used in metabolomic analysis? If so, how many milligrams?
Where is it first? Can plant extract be used in the metabolomic? Yeah, yeah, this is okay. Now it's also, instead of plant material, yeah, I want to do metabolomics of extract. It depends. If you don't want to do extract, why not? If you are using same metabolites, now is when I'm collaborating with Brazil, it's impossible to collect the plant material from Brazil, right? Because it's a Nagoya Protocol or based on regulation of Brazil. I cannot bring any sample outside of Brazil. In that case, always Brazilian group, they extract the sample methanol. Oh, this is young guy. Brazil, extract. Then, as long as you have a certain number of extract, for me it's very fine. Yeah, it's fine. As long as they use the same extract, yeah, methanol or methanol water, whatever, then it's okay. You can use it. But always keep in mind, some extract can have some lifetime. Yeah, so it can be rotten or not. And second one is, now instead of chemotaxonomy or physiological approach, I'm interested in food stuff, orange juice. Like instead of orange, I'm interested in orange juice. Then this orange juice, many main part is orange, but also there's artificial compounds are there. Then extract can be used depending on your goal. Whether extract is allowed or not, this is important. Also, I told you, when you do plant metabolomics, you go to the field, mountain, you have to collect the plant and quenching or something like that one, and then you keep the long time in the you keep in the fridge. That cases. Or regional plants on the market, Indian market, you collected the plant, but you are not interested in the chemotaxonomy itself, you are interested in this side, how to apply this. Then you can use dry material or extract this. So always depends on how can you apply, what do you want to do? That's it, you have to question to yourself. That's the answer. So there is no rule. I have to use this one. I have to use this one. No, depends. Would you ask Lucy? Lucy, whether it's sure?
She says yes.
Yes. Okay. Now, to the third step. The first step is we did it. First step we did it. You learned it. You learned it by chemistry. What kind of compounds it is. Why we have to learn chemistry? Learn biochemistry? Because it's basically, if you target metabolites, you have to know target of metabolites. But second question is second reason is which I mentioned today. Any kind of analytical techniques they have a limitation. We cannot detect all the metabolites, although we aim. Unfortunately, all the metabolites are linked each other under the name of biosynthetic pathway. So that's why you found the flavonoid, the major components. Then this metabolomics data can show maybe phenylpropanoid, chalcone synthase, or others can raise some question to you. So this is the question. That's right. Without information or without knowledge of metabolites or phytochemistry or natural product chemistry, probably you just use only the data which you got from the analytical technique. But if you have a phytochemistry, you learn this hidden part. So that's why nowadays, or many instruments, particularly for mass spectrum, when they have a data, metabolomic data, they selected all the identified compounds and they are integrated. They are integrated to known biosynthetic pathway from CAC. Then, of course, biosynthetic pathway we already know 100 steps. Then one step, second step, third step. Then you can imagine how they behave this one. In that context, you need it by phytochemistry. That's why I gave you the first one. Second one is I did a sample preparation extraction. You have to take out the sample from the matrix if they are ready for analysis. So that's why there is a benching, work, extraction, work, whatever sample preparation you need. It. The conclusion is depending on the sample, you have to optimize your extraction work strategy. And also, even same sample, as I mentioned, according to Lucia's question, depending on the work, depending on the work, sometimes you need a kind of replicate, sometimes you don't need, rather you need a more number of samples. That is now is the time you have a solution. You have to analyze, analyze please. Yeah? You have to analyze compounds. Now this coffee, now I extracted. What kind of compounds it is? Now third step. So caffeine, you already we don't have to measure caffeine because who knows this one is the caffeine. And any kind of analytical techniques, any kind of analytical techniques, there is no difference. Yeah. Actually, mass is not what the metabolic profiling sometimes used. Only difference is metabolomic chemical profiling is different direction. I want to see all. This is the thing. Of course, we cannot get this goal, but at least our goal is to get all the metabolites. Second one is I don't care about the mass, I don't care about the NMR, I don't care about the IR, but my goal is here to know, or even more is scientific question. So you don't have to stick on one method, you don't have to stick on one metabolite, but I will have to stick on what's your formulating question. So analytical technique in metabolomics, there are a lot. So analytical methods for metabolomics is next step. Our goal is in this stage, metabolize in your solution, your hamster, collect as many as possible. This is now you are hamster, you are not scientist anymore. Become scientist, right? Collect the data. So requirement of analytical techniques in metabolic profiling is first one is broad coverage of metabolite. You understand this one? Yeah. Because I'm targeting all, which means on target domain. I have to any kind of detection, you have to any kind of metabolite should be detected in my single run. Second, quantitative. What's the meaning of quantitative? You did too much today. You did too much today. So why I have to use the what's the meaning of a quantitative?
Because the law of what you have.
Quantitative in this case is any kind of a signal must be proportional to the concentration. That is clear because some analytical technique I measure 1 milligram or intensity is 1, 10 milligram sometimes 1, 100 milligram 1. This is not an issue. But for the qualification to identify, it's not an issue. Like your case, when we are doing 2D animal, 2 dimensional animal spectrum, like a COSI or HMBC, HSBC is HMQC. Those one we cannot use for the metabolomic profiling. Why? Because they are not quantified. They are not quantitative. Signal intensity must be proportional accurately to the whole concentration. But some analytical techniques like 2D NMR, or even in the HMS, ion trap cases, the dynamic range 1 to 3 sometimes is a very narrow range. So that's why dynamic range is very, this is related to the dynamic range. Quantitative. This is the requirement. You understand what I mean? Huh? Yeah.
Mm. And that's it's important how much the model can analyze. Always you can make this correlation of the peak area and the intensity, the sample, the concentration, because the compound ionize more easily.
Yeah, this is a, but anyway, it's outcome. Now it's a 1 milligram. Look, this is a difficult question is, now this one is a flavonoid. This one is sugar, for example, yeah. Now in mass spectrum, when I injected 1 milligram, 1 mole is here, injected, Animal case is 1 mole of flavonoid, 1 mole of signal, they are same intensity. Right? I can compare in the one spectrum, this signal flavonoid, this signal sugar. When they compare, it's higher. This one is high molecular. But mass cases, as he mentioned, is not exactly more concentration. Flavonoid, yeah, flavonoids very well ionized, very high signal. Sugar case, it's very difficult. Even you put the one small signal. Now, based on this one, it's small signal, it's a higher signal. I wouldn't say flavonoid higher in this case. That is a ionization problem. But this one is spectral sugar. This one is sugar. This one is here. This one is here. I can say, okay, in mass spectrum, this one is higher concentration compared to within sugar case. But this case is mass as a problem because of ionization problem. But this one is also quantitative. But what I mean is mass spectrum, ion suppression. Sometimes if you draw, if you inject in the dirty sample, you have a cleaner sample, a cleaner spectrum. This is ion suppression. Ion suppression means if you have a very dirty sample, big signal suppress all the minor signal, which means there is a limited dynamic range is there. So now is animal case, as long as it is soluble, dynamic range 100 times is no problem. Or even HPH UV, very big dynamic. When you do calibration curve, 1 to 100 more is no problem. But LCMS case, even triple port, yeah, maybe 10 times. Within 10 times, it's okay. Ion trap cases is much less. So that's why in ion range. Then how can you do this one? You have to adjust sample concentration. This is quantitative. Quantitative mass, yes, very quantitative, but within range. That's the dynamic. Quantitative. What's the meaning of quantitative? Now you have to explain. Yeah, you have to explain to me. It's because I have a problem with my voice. Why I have to?
It is smooth and
Very nice. Yeah. From the quantitative is a concentration. Qualitative means from the signal. Can you guess the structure? What there's a potential or not? SMS 300 molecular weight 300 1 to 1 to, then it's easy. Why? Because you can look up in the Google or some database of flavonoid comes out. It's a qualitative. Based on data, whether there is a possibility to know the structure or not. SMS is one. NMR 7 ppm or this one to know the structure. But when you do some higher spectrum, or when you do HPC UV spectrum is not really quantitative. Based on UV, you don't know the structure, some except for some compounds. That's not qualitative. Then, in that case, probably this quantitative is maybe it's not necessary for fingerprinting. I'm not interested to identify the compound. I'm interested whether it's the same or not. But for the metabolic profile, we need it is qualitative. This is clear? Then, reproducibility. I need a reproducibility, right? I don't have to mention. Because if you do one time experiment, it's okay. If you are lucky, if you get the nice spectrum, I don't care about this. Like a 2D animal spectrum, sometimes. But I need a 100, 1,000 separate. Exactly it's the same response should come out. Otherwise, we cannot trust the data because anyway, the next statistical analysis we are using intensity. But if intensity now you add in 1 milligram, sometimes intensity 100, sometimes intensity 1, then we cannot use it. That's easily reproducible. And signal robustness. What's the signal robustness?
when you change the parameters or the conditions and the signal gets.
So now is singular reproducibility means is the same is more or less quantitative feature. Robustness if is, for example, it's a simple question. A simple example is if retention time is every time changing, sometimes 1 minute, sometimes 1.1 minute, then variable length is completely changing. But That is signal robust. Of course, there is no perfect method to show the 100% signal robustness, but this case is less. In that context, NMR is rather better than mass spectrum. Actually, not mass chromatography, because mass itself always same. 300, 1 to 1 to 4 decimal, depending on the filter, always 1 to, but always varies. Some people think, oh, this is not signal robustness low. But actually, molecular weight never changes. Not never changes. Less changes. Chromatography part is changing. So that's why always alignment, the new alignment, the SMS methodology is not for the mass part, it's for the chromatography part. So clear? And short time for the measurement. I don't have to mention this for the money, but then also time. If you like SMS, how long does it take? Usually one run, at least half an hour. Because watching it only half an hour. But GCS, maybe it's also is half an hour or 1 hour. Then how many samples can you handle? In a day? 8 hours working time, or you don't sleep, then maximum is 24 samples with all the samples. Yeah, right? And then what? How much we need it? Maximum 5 and 10 minutes. Completely different. So that's why if you have a more number of samples, like clinical studies, that's why you prefer the NMR first. That's clear? That analytical tools available for metabolomy, you can name it. Now is chromatographic based one. Chromatographic based one, HPCUV. No, sometimes can we use HPCUV? Yes, we can use it as long as bigger thinking cases. No problem at all. IR, you can use it. HPC, IR also is possible. HPC, mass, yeah, ELST, which means what's the ELST? Decorative light scattering detection. Before, actually in all the time, sugar, sugar does not have a chromophore. So that's why UV is the most popular analytical tool. We cannot analyze sugar. So that's why they developed RI, reflective index method. But it's too sensitive. Too sensitive means too very. So that's why at that time they used evaporative light scattering detection method. Then sample has to be very small larger, then become foggy. Then they gave a laser and reflected, they measure this one. So this is not better of this one. Reflective method. And GC, FID, one of the best quantitative method. Compared to quantitation is GCI FID is much better than GC mass in terms of quantity. And NPD detector and TLC, UV TLC mass is possible, and CE, capillary electron press. Any kind of method is possible. And non-chromatography method. Non-chromatography method is we are using only detection. What's the problem? And all the signal is one spectrum. If you introduce the chromatographic system one by one, peak by peak, you have a separate signal. But non-chromatographic method, NMR, you can use it. NMR, in metabolomy, of course, HPLC NMR is possible, but usually NMR is being used resistant. You measure very complex spectrum of stuff. In IR, infrared spectroscopy, when you can apply this IR, this one is a kind of fingerprinting, coffee. The most expensive, one of the most expensive coffee is, they said is, there are several coffees, what's that, Blue Mountain, Guatemala, but there are so many things. Coffee classification, yeah, coffee classification you are using, and this IR, two advantages I'll explain later. First, we don't have to make a solution, solid state, we can measure it. So coffee bean, powder, you add it, and also, it's 1 or 2 minutes, it's no problem. Now, you have a pharmaceutical, big pharma, you produce every day tablet, yeah? But you want to know which one is outliers. This is very important one, otherwise it will cause a lot of problem. Should I use SMS? It takes 1 second for 1 hour. Or NMR? No, so how to just IR scanning the fingerprint method, this IR is a problem. Or sometimes you are using Raman spectroscopy. It's a vibration. And also IR is very robust signal. Before measurement, before NMR, IR is being used for the chemical fingerprint. So they said is whether this structure is or not. If you compare IR exactly the same, then it's compound the same. But UV, some compound they have the same UV. NMR sometimes the NMR is more close to the closer to the IR, but still NMR sometimes is a problem. Mass even worse, but IR is still. So that's why they use this one is metabolic phenol and mass spectrum direct diffusion. Have you ever used the direct diffusion class? I use many cases protein analysis because protein analysis they are directly instead of this one add some purification protein they inject very slow with the the pump. This the series pump they added this one. Some metabolites, if it's very valuable compound, what you think is not very much problem with the ion suppression, like the CEA, capillary electrophoresis, the cerebral spinal fluid, maybe you can use it. Plants, we have a similar centers. Which one it is? Plants, I told you, so biofluid, solid, well, there are many kinds of biofluid. But in plant, there is also, I told you, leaf, root, flower, whatever. There are some liquid sample. Flowing cell. Do you know flowing cell? Yeah, flowing cell is like a liquid, yeah? All the, that one is when you collect it, you can use it with the direct injection. Or sometimes with the very good chromatography. This flowing cell, what's the sample? I didn't include this one. This flowing cell from plants. It was a big tree. I small liquid, yeah, from cell. And this one always they adding protein. Why? Because stop enzyme division, and then sooner or later they use HTS.
For C, you did mention ECD get and NAD and
So I forgot.
no,
I forgot.
and ER, you said it is very robust technique for fingerprint.
Yeah.
And any IR near infrared, it's the same.
NIR, do you know NIR? Near infrared spectroscopy. IR, here there is a UV, short wavelength, and here is a visible. Yeah, visible around 220 nanometer, 200 nanometer, 360 nanometer. After that, it's an IR vision, right? And in between, there is an NIR vision. IR vision, IR, do you know? IR, there is a wavelength. Always in the nature, if you give a certain frequency, there is a, in the atom or molecule, based on, based on the movement, they have a different the frequency preferable. For example, if I give a UV 200 nanometer, I cannot activate the proton, whatever. Only electron is moving because electron like wavelength. When I give a IR, then it's atom movement like a vibration. Yeah. So then is this one. What's the NIR? Do you know NIR? What's the target? And NMR cases, if it's a radio frequency, very low wavelength, like 1 or 5 meter, if you turn on radio, then proton, nucleus, they are observed. So this is a different. But NIR cases, when they added NIR, then, do you know NIR? This one is like a microwave. The hydrogen bonding. Hydrogen bonding, like if there is a hydrogen bonding one is activated in this case. So that's why like a polymer type of the compound, polymer conjugated with a small molecule, they are activated. NIR also is possible because any kind of a sample they have a polymer and interact with a small molecule, NIR also is possible. But it depends on the target. But NIR, Raman, well, IR, we call it is a vibrational spectroscopy. That one is good for chemical fingerprint. So recently, HPLC NMR, NMR that just shows is possible. But this HPLC NMR is for the qualification. Qualification, we can use it, but for the generating the metabolic data, I think it takes some time because one sample measurement, how long does it take? It's more or less 1 day. One sample 1 day is too much. So now chromatography method for metabolism, each patient usually target is metabolized color. And GC no color. TLC is general, but capillary electrophoresis is ionic, and CPC, centrifugal partition chromatography, is general. The producibility, resolution, it's all different. Yeah. When you choose TLC, okay, I can detect many compounds, but resolution is not there. Can I use this one for the fingerprinting or not? Maybe it's doubt. But sometimes we can use it. And when I use HPLC, you have to think about what's the target, because usually HPLC we are using no CAP color. This CAP color is actually good for the polar compound, but if you have a lipid or carbon or other compounds, you will lose the information. So that's why, in that case, you have to, if you choose the technique, then you have to choose what's the limitation of this technique is very important. Capillary electrophoresis. Now you have in your lab, you have a capillary electrophoresis. I want to use this one. But what's the problem? You can detect only ionic compound. You don't have ionic, non-ionic compound, probably you cannot detect it. So that's all these pros and cons you have there. And among those one, actually metabolomics starting with the GCMS. It comes around like that. Then GCMS, GC shows better resolution than HPLC. That's you agree? Because peak is sharp. Why is it better? You know, HPLC is a little bit this one, but GC is very sharp. Have you ever thought about this one? What?
The length of the capillary column.
So why not we can use capillary column with the HPLC? Some years ago, we used the capillary column. And even capillary NMR is also possible. Because HPLC is interaction both sides. Column resin, solid phase, and liquid phase. So that's why in HPLC you always use mobile phase and stationary phase, right? But gas chromatography, you never use mobile phase. Instead, we are using carrier gas. Carrier gas, helium, hydrogen, nitrogen. Now, when I'm moving HPLC here, here. But GC column, GC cases, only I'm interacting with the polysiloxane here. And helium is like driving, moving. But then resolution should not be good, right? Resolution should not be good. Instead, gas chromatography, they are using another factor, temperature. That's right, temperature is so that's why usually inherently, GC has a sharper phase. Then electron impact or chemical ionization is used in GC. Still, we are using EI is the best method. Best method. As I told you, EI method means after gas compounds eluted from gas chromatography, then there is no solvent. Helium is evaporated, right? I am going to EI spectrum. Then what's the first requirement in mass spectrum? Ionization. To make an ionized, I gave an electron 70 electron volt. Then one lost. That is ionized, you can detect it. But this 70 electron volt is very strong. So that's why all the fragmented signal, if I put here, then all cut. This is a problem, right? So that's why we couldn't detect the molecular ion in the GCMS. Still we are using PI. So they developed the CI. What's the CI? Chemical ionization.
Run a needle.
Huh?
Use the run a needle for ionization.
It's like APCI base, it's an ESI APCI basis. But this one is a CI means we have another medium gas. I don't want to direct ionize this compound. Instead, I have a methane or ammonia. I ionize this gas and then this ionized one indirectly. On fact, this one we expect this power is low. Then probably it would detect molecular ion. But wait, even though we detect molecular a little bit better, but it's not good. But still, when you purchase the GC, EI, CI is more the possible. But they 99% they want to use the EI because CI first. Our aim why you want to CI because I want to see molecular ion. But it's not enough. But fragmentation is less. We cannot use this database, and also there is not very much reproducible fragmentation. CI is not much used except for a few cases. Now instead, sometimes they are using APCI, GC is also possible because glucose in German is what we use, the APCI mode is also possible. And commercial database, GC, one of the advantages when you are using commercial database is available. But this database is a very plentiful source for the chemical identification. This database algorithm is different. Because most of LCMS is based on molecular adapt ion with some fragmentation or some usually the M plus H, M plus Na, M plus K, that they found molecular ion, they search compound. But fragmentation, GCMS is very robust. They are using this fragmented filter. How much is similarity there? This one is more important. And the limitation of molecular weight, is more or less not 400. Actually nowadays it's up to 600. But in YouTube plants, there are more than 600, like 800, 900 subcoding or glycoside. So that's why when you are doing GCMS, you will lose the information of many parts of like the secondary metabolites. And generally for volatile metabolites, because inherently GC can analyze only gas-phase sample. But gas-phase sample, compound should be gas.
Yeah.
Gas sample. So that's why this one was developed in oil company like fuel cases. But when you are using gas phases, yeah. So that's why still we are using. Have you heard about the headspace? What's the headspace? Headspace. Headspace means now is when you are doing some volatile, like a plant, you grow here, and then I put balloon. Then plant is inhaled or exhale. I collected this balloon and I moved the shishi and this gas. It's very easy to be injected. Well, of course, nowadays, by the SPME method, because it's to concentrate the compound. But anyway, at space, it's a volatile compound. But in this case, the most common application GCMS to metabolism, we are the best method, as I told you, is a primary metabolism. Primary metabolism means sugar, carbohydrates, amino acids, organic acid. But carbohydrates, melting point, I don't know for boiling point, melting point is around 200 Celsius degree. And it's very full of compounds. Polar means there are more weight. This one is not volatile. So that's why to make those compounds volatile, we use TMS derivatization. There are hundreds of TMS delimitation. Why we use the TMS delimitation? Because it's the easiest method, it's a simple method, reproducibility is very nice. There are hundreds of methods of derivatization, methylation, phenylation, whatever. But when you are doing most kinds of derivatization, yield is not 100%. TMS is very nice. Very nice. Then after TMS, then sugar TMS, yeah, all the TMS then become volatile. But become volatile, you can detect it. So that's why GCMS is volatile. But I have a question. Even sugar, organic acid, or steroids, sometimes steroids, if they are injected, you dissolve in the exhale. Well, some acetone, you inject it, but sugar chemistry derivatized one is boiling point, yeah, boiling point is not less than 100 Celsius degree. It's a lot. What I mean is, for example, cholesterol. When you inject the cholesterol, without chemistry derivatization, you can detect in gas chromatography. You can detect in gas chromatography. But cholesterol is not gas, right? Why? How can you detect it? Because gas chromatography, any compound should be volatile, right? Yes, otherwise they are moving to the color. But cholesterol, they are moving, even though they are solid. How? Do you understand my question? Even after chemistry derivatization, boiling point is 25. Why?
So, and alcohol, that's now from
Because phosphoric is what? You know, in the GC color is a vacuum, almost vacuum. They reduce the temperature, the pressure, then which means boiling point is going down. So that's why even it's in the atmospheric pressure, this one is a liquid, but when they are going to GC color, it's a very low pressure, it becomes so that is the kind of thing. Yeah. Okay. Then here. Now TMS derivatization. Here, one of the example of TMS derivatization is here. This one is protocol. More or less, when you do GCMS analysis, this one is general protocol developed by Max Planck Institute in Germany. So here, now methoxide in pyridine. Yeah. Because normal chemistry derivatization is pyridine, you dissolve in the compound, you add in the TMS. But in this case, methoxide, because this methoxide blocked, yeah, blocked ketone. So ketone is always reactive. After that, you add it here, 90 minutes, 28 degree, and MSTFA, one of the TMS reagent, you can use it. But some people, they are using ESTFA. Doesn't matter. Then you can use it, and 30 minutes, 25, and then you can use it. That's the key point. 2 point. First point is methoxide, period. And then MSK. In this TMS derivatization, you have to be very careful. Sample should not have any drop of water. Because if it does, it's water, then this TMS derivatization is salt. It's blocked. Yeah, you can follow this one. But variation is here. So usually in our lab, I made it, methoxide, I bought it, and so 40 milligram, yeah, 40 milligram per ml, I made a stop solution. Instead of PDD, we use. And now it's mass analyzer. After, here, mass analyzer means after ionization, we have to analyze, like a probe. Yeah, this case is here, quadruple. What's the quadruple? The same as the HMS. Quadruple means after ionization, the ion they pass one, two, three, four rod. Each rod has a changing the voltage. So that's why. So depending on the voltage, the path is different. We are changed. Then you can separate all the ion based on molecular weight. But this one is the first, actually first generation of quadruple. Now you heard it. triple quad, right? Triple quad means there are three sets of triple quadruple. One quadruple, second quadruple, third quadruple. Why we need it? Because after each quadruple, you can select one ion and then you can send to the next. We call it, it's a S. A triple quad is most common nowadays. Single quad is a rather cheaper one. Triple quad is quite nice for the quantitation, targeted analysis. And ion trap. What's the ion trap? So like HMS, GC ion trap is possible. Now, instead of a quadruple, they have a trap. They collected all the ions in the trap, and they changed the ions. They released one by one. It's an ion trap. It's a cheaper method. Advantage is actually if you want to do mass, you have if you have a two mass, mass, you need another quadruple. Three mass, another quadruple. But ion trap, ideally, you can do then 10 mass is possible. They say it's not pure mass. Here, now it's a lot of ions here. Now you detect it, and then now I'm interested among those 300. I threw it away, all everything. I only left 300. I give additional energy. Then there is another one. Then I'm interested. The second mass is 200. Then threw it away. 400. Actually, this ion trap go more with the cheaper machine. But the problem is this ion trap is quantitation, narrow. And triple quad, I mentioned this one is three set of quadruple. And magnetic sector instrument, this one is also quite expensive machine we are using. And laser time of flight, toughness. What's the toughness? Time of flight means, then depending on the ion, heavier one is further, and light one is when you throw the stone, of course it's the opposite. When you throw the stone, heavier one is very not far, light one is going fast, going further, right? That is like this one in the time of flight, This one, of course, it's heavier is going there, but quality itself is not. It's a mechanism. Of course, they have pros and cons, but quality itself. Top is 4 decimal, more or less 3 to 4 decimal is possible. For example, now molecular weight because of isotope effect, if you have any trust value is 300, nominal mass, Now you type it 300, the dictionary, natural product, how many compounds are coming up? 100,000 compounds are coming up. You don't know which compound it is, right? But if you have a high resolution, 300, 1, 2, 1, 2, if you type it 300, 1, 2, 1, 2, then you can get only one compound. So that's why this accuracy, high resolution is very important. At least this high resolution mass, we need this kind of top mass. Understand? So that's why now you heard it many times. HMS, your HMS, what is your HMS? In your lab, which kind of HMS do you have? Excellent. HMS is a Q-top, right? So they said it's a Q-top. Then you can understand. Quadruple top. So there are two detectors, and let's analyze is an integrate. Then Fourier transform. Have you heard about the Fourier FT-MES? What's the FT-MES? The same as NMR. Now, Fourier transform, FT-MES, you need the magnet. Now I'm ion. Ion means charged one, right? Charged one. All the charged material in the magnet, charged material in the magnet, they have their own frequency. Right? That's the rule of the nature. I didn't make it, God made it. All the ionized, like protons. Proton in NMR, in the magnet, they absorb frequency. And also ions in the FT NMR. Here, Then based on this one, some ions like this cosine or sine curve, some ions sine and cosine curve, some ions like this, all kind of a mixture comes out. Then we apply Fourier transformation, which are being used in NMR, which was developed by French mathematician 17th century. So we apply. So that's why we developed one everything. This one is a really accurate test, but we cannot apply with the limitation to connect with the HPLC. Instead, we are using more often orbital. Similar mechanism is a more accurate test. You understand what I mean? So there are three parts. Chromatography, how to inject your sample. GC, LC, or direct infusion. This one. After that, what's the method? Ionization. You have the ionization. And third one, mass analyzer. Any kind of mass is a paper of this one. Yeah. Now, sometimes, maybe nowadays in animal, of course, in animal is worse. Yes, they are using too many jargon, abbreviation. Yeah. If you study computer students, they don't understand, right? So ESI quadruple means ESI ionization method, and then quadruple mass analyzer. Here, mildly, how to ionize mildly and top. Then now his mass in his lab, he has a Q top. But usually nowadays, in LCMS, we are using ESI, almost 99%. GCMS, we are using EI. So that's why ionization method, we take out the name. Q-top means they are using two detectors, two analyzers, quadruple and the quadruple and top. Yeah. And ESI, electrospray ionization, APCI, atmospheric chemical ionization. What's the difference between them? This one is not being used often in GCMS, but this one is ionic kind of ion. I explained to you EI. Yeah, right? I explained to you ESI yesterday, passing the nodule. Then what's the APCI? APCI, when you buy SMS, always APCI is option. You can change it, but we are not using often. What's the APCI mechanism? It's the same as, similar as EI and CI, ESI and APCI. That's usually we need about atmospheric solution. When you do ESI, there is no source for the electron volt. Why? Because when the sample is passing through very narrow nodule, they become fog or mist, they automatically ionized. Yeah? Because my solvent is water or methanol cases. Very transiently short time, I'm ionized. So it's very soft ionization. But sometimes when you are doing lipid material, like fatty acid, fatty acid which are not soluble in water, then it's not enough. Even when they pass the nozzle, they are not ionized because water or methanol does not help to make me ionized. In that case, there is a corona. Have you heard about them? Corona, another special devices, they ionize the solvent because now I injected, instead of water, I injected the chloroform hexane because lipid is not soluble chloroform hexane. Yeah? Then I injected the chloroform hexane. Chloroform hexane is not polar solvent. They cannot make the sample in the ionized. Then I can give a corona devices. I give a electrovolt chloroform. Then chloroform hexane is in short time they are ionized. They work like water. So that's why they can make what they need. But ideally, APCI looks better because it's better, but APCI limitation and robustness in the ESI is better. So APCI is sometimes using and multi. What's the multi? It's for the big molecule, So it's a kind of soft ionization in the big molecule. Instead of ionization directly, I put this one in the matrix, like so. Yeah? And then I gave a laser to the glycerol ionized. That is what two compounds ionized. Its working outcome is very well with the polymers. But binding cases, have you heard about the H-based binding? LCBR binding drug? No, because it's difficult. Binding usually is an isolated compound or without chromatographic system we are using.
Uh, for if I work with the donors, do you think APCR is enough, or is there a way with APPI?
It's a depending on the machine. Actually, it's a really vendor dependent. Now the Metabolomics platform is a AB science, yeah, science, they are using the API or APCI, something like that. But I have no idea how much, yeah, we need it, enough or not. It depends. Really depends. Lipidomics cases, usually lipidomics instead of a plants is we are using more inflammation studies in the clinical studies cases, right? Then the thing is APCI, of course, the more is better. And also, you mentioned yesterday ion mobility, right? In these cases, ion mobility sometimes is helpful for the lipidomic cases. Lipid cases, well, then APCI is matter of sensitivity, how much they can sorry, ionize, yeah. But lipidomic cases, the problem is not sensitivity, lipid is a lot, right? Says not sensitivity, it's a resolution cases. Right? So in that resolution, it only mass information is not no ion mobility information is a little bit important. Do you understand my question? So that's ionization. Even the glucose, azure, whatever, depending on the machine, it's completely different one, right? That's why I cannot say it. Any question? Yeah.
I don't know if I understood this well, but did you say that each APCI method is better for human molecules?
Binding is a big molecule. Binding is a bigger molecule. But big molecule like protein or big molecule, protein is well ionized by mild ionization. But lipid, non-polar material, ideally, is well ionized by APCI. Most of water-soluble compound is well ionized ESI, but in practice, practical situation is ESI is more often used in the development. That's my comment. Okay?
How about the models? It's difficult to introduce the information of machines using microscopes.
You multi, but multi, which kind of multi, as I mentioned, is for the mainly for the polymer. Small molecule have a little bit power for the ionization power. Small molecule is not very well ionized binary. You know binary image. The binary image now is you have a sample, after matrix, they scan, they all detect the compound. Even binary can detect a small molecule, but it's not really a fully ionized basis. Instead of this one, resin or resin, or those kind of small molecule targeting immediately is being used. And also binary cases, as you mentioned. So depending on the matrix, the quality is different. And second one is sometimes if you have a multi, then I was discussing with the people. Oh, if you are targeting with targeting the one small molecule, you don't have to use it. You don't have to use the matrix directly related to the sample position.
But if you use, you can analyze a small molecule in the leaves, for example, if you use mode of energy, then you can detect a small molecule.
But image, I mean, is well ionized polymer, but it does not mean small molecule cannot be detected, but not fully. That was my point. And also image, yeah,
What we quantitative analysis.
no, no. So that's why it's like a small molecule quantitative. It's like image basis. Sometimes when you make a photo, photo, when you make an iPhone photo, it's not quantitative, but it's no problem to recognize. And also targeted analysis. For example, now imaging technique, why is it important? One is our current metabolomics. I think you mentioned a long time ago. This metabolomic, as I said, I measured that. It's kind of snapshot. Now I put the snapshot. But now the problem is 2 points, 2 factors we cannot resolve. Second one is time. Now you look like today, this one. Tomorrow, who knows? Time. That's why time point we need like a film. So this one is rather is solved by proxomics. Another one is, as he mentioned, this one is only the targeted analysis. But if there is some infection, now you are interested where plants live, or if it's a leaf, then you try the infected, like by the some part is infected. What I'm interested in that part. In that case, you can use this kind of imaging, lazy. But as he mentioned, any kind of imaging technique still is a quantitative issue. Now you want it like what's that? Dark mass. Have you heard about dark mass developed by J-Roll? Yeah? Dark mass. Now it's sold to Google, yeah? Because they're a small company. Dark mass is dark mass. Dark mass means you can directly give energy to the surface of a material or the metabolized ions. But this one is not quantitative. So only semi-quantitative. But semi-quantitative is nothing. So this kind of imaging also is good for what? Pesticide detection from the surface of orange. Sometimes they are using pesticide. And now they heard it. Have you heard about the GC times GC? Yeah, what's the GC times GC? But now is I have a doubt whether we have to use it this one or not. But anyway, when math development was not enough, they using GC times GC. For example, you have two columns. You have two columns. When I use 30 meter column, you analyze this one. But as we discussed yesterday, one peak is not necessary to be one compound. Two compounds is a mixture. The second column is like a shorter one, 5 meter, 5 meter. Yeah, you add it. That column, that overlapped one, can be separated by second column. So this times this. Here. Now, the second column is here. Now is here. When you do this one is almost different, but it's just separate. But this one is being used quite often. But the problem is, what's the problem? Data size, because GC, and like LCMS. Now, LCMS, GCMS is already, if you have a full spectrum, how many data size? It's around one sample, it's a full size, it's sometimes a few gigabyte. But GC times GC, one more GC, that is a lot. That is an issue. So in that case, maybe you can see some identification basis. And now, range of mass detection. Now this one. It's kind of my general one. ESI cases, polar compounds, ESI MRT can detect this range. APCI, more or less maximum, they said, I don't know, around up to 1,000. And GCMS, they say around 700, this non-polar. But sugar is polar, but this non-polarity can be improved by chemistry demonstration. This is more or less, but ESI is the most common ionization method in the mass spectrum. So ESI, APCI, I have already mentioned very clearly. ESI is APCI is almost the same, but APCI need an additional device to give an additional electron voltage. And LCMS data, it's like LCMS data here. So this one is what's that? Detention time. And then this one, molecular features, molecular weight, and intensity. So that's why H-mass cases, what H-mass cases, three-dimensional. Chromatographic axis, x-axis, and this one is axis, and then here. So that's why H-mass, when you make a variable, you have a two name. You understand? Now we should think about gradually about the statistic. Now you pick 300 is comes out. 300 is not enough. When it comes out in chromatography, 1 minute 300. His name is 1 minute 300. Your name is 2 minute 300. Something like this one. So that's why now we are using two names. Yeah, two names, surname and first name. This one, two name cases. But NMR cases, no. It's only one name. Young is enough, not Young Choi. So if you use two names, which means it's a data size is much bigger. Right? So that's how much is it? More or less I can explain you. But so here. So really basic of the sample, the processing of data is looks like this one. Here, your data, sample, and proceed, and retention time is here. Yeah, they take out. Like this one. Now you have if we have a two-dimensional data, chromatography data, then this one, two, three, intensity. That is enough. Young, this one. Fatima, this one. Gilberto, this one. This is one name is enough. But HMS case is two-dimensional. Yeah? That's why to make for the next statistic, how to make it this one. HMS case is detention time, and quantity. So now, if you want, give a name of this one. Now, his name is Maria Fatima. Young Choi. Now, you understand? Two-dimensional, three-dimensional data. Now, the reason why I told you why GC times GC is so difficult, there is another name, Maria, Fatima, Nasalva, or something like that. That's it. Of course, to put more name is fine, but now we think about the efficiency, the data size. But basically, data processing of SMS data, it looks like this one, time this one, like this one. Scale. You understand? Always now is metabolomics processing part. How to give a name of the variable? How to give a name of variable? HPS UV, okay, intensity 1, how much UV intensity 100. This is a 1 minute is a name. Intensity 100 is a value now using for the statistic. Yeah? And now is mass problem of mass-based method. It's big data set. Here, metabolomic NMR, 1 gigabyte. No, it's not true. Actually, if you do proton NMR, it's only a few kilobytes is imported in the blood. Few kilobytes. But now, maximum metabolomic XC data mass is 60 gigabytes. Now, you have a sample, 1 year. You cannot use your laptop computer. You have to use a super, not matter of efficiency. You have need a storage of data. And also another problem is nowadays I show you data. All the data processing, processing data is the processing method is developed. The problem is every day new method is coming out. Every day new method is coming up. Now, to save your space, now you have only process data saved. Now, today I found a very nice algorithm, but I don't have raw data. This is a problem. It's like, then is the issue is how to store the data, smaller scale. And problem, not problem, actually, mass data experiment, raw data processing, the general process, very old, the basic one. After experiment, raw data processing and filtering, feature detection, alignment, validation, data analysis. This is any kind of data processing of SMS, XGMS, or metal line, whatever they follow this one. Here, and also animal case is one of the advantages. Animal is usually 99% we are using one. Profile, you can use profile, no problem. Even though FID from JOL is no problem. But mass data is not like this one. AB science, as you know. What you water, thermal. But they have own database. They have own database. The data format cannot use it. So that's why to make an open source for the data processing of HTML, first step is to get the common data file. Then this was a NetCDF data. So any kind of vendor, you can convert it to this data. So for example, if you measure regular, then convert to this one, then you can try with SGNS and then mine or some metal line basis. But NMR, we don't have to call it, right? Proof of FID basis. And now its first step is filtering, centralized processing merge data comes to same thing and binning to fix them and value and removing chemical and atoms and noise. Now, here, looks like this one. Low spectrum always looks like this one. Now, then filter and if it's a filter now, let's look at this one. Now is I don't want to explain your algorithm because algorithm means you can use any kind of algorithm. But question now, original data is this one, which means there are two possibilities. Because of HPFC, and because of mass issue, this one is like a one picture like this one. Another possibility. Probably all these peak might be different. But this one peak contains several, can be several signals. So if you have very strong filtering system like this one, then you will use the information business. I cannot say which one is more good or not. Any kind of algorithm or processing data, if you have a very strong algorithm, nice, looks beautiful, looks nice, but we probably you will lose the information. There was a point. And second step is a featuring detection. Featuring detection means, let's say simple, which signal is real signal. Right? When you measure the HPLC data, the SMS data, now I detect number four. Four signal I detected. But ideally, this all four must be from my sample. But also possibly some signal from your instrument, right? Some signal supposed to be. Yeah. How can I remove this one? What's the easiest way? Yeah. If you simple way is remove, you injected the blank sample. Yeah? You inject the blank sample and then you remove. But sometimes both the signal is changing. It's not always it's coming out. Sometimes it's coming out. Then how can you remove this one? So it's not mass spectrum. There is some scandal or episode in Japan around 1978. There is an animal instrument. It was an animal instrument. Every time, every day, they measure. There is most signals coming out around 100 dBi coming out. They go I measure this sample, I measure another sample. Always is coming out some ghost signal which are not from the sample. Strange, but interestingly, this one is only sample when you measure 10 o'clock or 9 o'clock. Strange. Osaka, Japan. Do you know what's the reason? Because next to the lab of Osaka, there is a rail trains. Every day, electric trains they passing there because it's a magnet. Electric, they are influenced because signal comes out. That kind of process, how can I do this one? Each is the way it is the way it is. we measure the same sample several times. If it's a ghost signal, then it will be removed. This is one of the ways to remove the real signal. Yeah? But there are hundreds, there are several methods, many methods to remove, to select which signal is from your real from features. This is very important. And also, why I have to use, this one of the reasons is to save your data size. If you have too many dots, the data size is too big. Right? If you have a remove this one, it's not that big. Then data featuring detection is features should combine several ions for same molecule. Now, what does it mean this one? Feature means it's a featuring. Now, this signal is a modern ion. This signal is, for example, is a fragmented ion. Yeah? Of course, if they are always behave the same, I don't care. Problem is in mass spectrum is very sensitive. There are two ways. This one is very quantitative, but this one sometimes is not quantitative because it's mass. Then there are two ways. Among those one, first one is which one is which element is the mass signal fragmented ion from one molecule is one. Then among those one, I select only one fragmented ion which is quantitative, or I can sum up. That is a featuring. Featuring means, simply speaking, which mass signal is the representative of molecule. That's the signal. This is a featuring. Clear? What's your representative? Last or something like that, but yeah. My hair color like this. Okay? You have to choose it. Young Choi, what's the my featuring? Yeah, so I or something like that. That's only one form. That's it. Now a lot of signal comes out. Use. Then second one is which one is the representative? To characterize, they have to be characterized. To characterize your molecule. And requirements to the HNS method. So third step is alignment. Alignment, why is I told you alignment is nothing without mass spectrum. Because I use chromatography. HNS, liquid retention time. Retention time is always very good. You have experience with HPLC. You injected it. Today I injected 10 minutes coming out signal. Yeah? Coming out signal. But now, tomorrow, I injected the same sample. Can you guess this one is 10 minutes? No, sometimes 11 minutes, 9 minutes. Of course, if you are using only one sample is no problem because you know this signal, but you have 1,000 of spectra. I told you data processing is you put the name. Now he is 10 minutes, yeah, like Maria. But tomorrow he changed the Mario. Then it's a completely different one, right? That's why always alignment very important. Alignment is very important. How does it look like? Now original animal chromatograph, sorry, HPC chromatograph, or even GCC chromatograph looks like this one. Corrected, aligned. This is nice, right? It is all same. Sometimes his name is Mario, Maria, Margaret, whatever. But today, from now on, your name is Maria. Yeah? This is your video. What's the problem? It's the same as what's the problem? There are hundreds of walking technique, not walking. So like alignment technique. There's a mathematical algorithm. You don't have to know, but we have to know limitation of this algorithm. Yeah, this is what I mean is, yeah, also it's a strong line can cause activity. Now, this one is two signals coming in like this one, yeah. Now I think those two signals is the same. Yeah, I think you are Maria. Okay, I put the name, but actually it's not Maria. It's a Gilberto. right? That is a strong alignment. Sometimes code you lose the information. So that's why animal signal also fluctuates a lot. Not as much as chromatograph, but now it's 1 ppm, 0.99 ppm, or 1.1 ppm. Sometimes it's this one. And some people they want to apply this alignment algorithm to the animal signal like this one. The problem is NMR is within 0 to around 10 ppm. A lot of a signal is this one. Sometimes this kind of signal, if you align, then you lose the information. So some people are doing alignment. Then when I cannot suggest them to use this alignment animal signal, you are using exactly same variety. Like I measure only every time orange. This orange, this orange, this orange. Then probably you can apply to the alignment program. But now like your species cases, yeah, orange, potato, whatever you measure very different species. Now you signal like this one. You align probably this one might be different signal because in animal dimension it's small. Some difference can be different compound you align, then it's a wrong information.
Like, it is like a human. Like, for one human, can I use the lines for the NMR sheets?
NMR alignment, I will show you later. And instead of this algorithm, I will show you how to align NMR. We are using meaning data instead of meaning data. And then express in glucose, they are also using meaning data. Yeah? You understand? Yeah? Of course, you understand. I didn't keep a very difficult theory. Yeah? And now it's alignment, like a chromatograph. It's not alignment. It's not only for SMS. Sometimes now some people they want to use HPHUV for the polyphenol fingerprinting cases. Play this one. Then okay, HSP. Yeah, can I use HPHUV? HPHUV for the metabolic fingerprinting? Yes, of course. But requirement is you have to use this kind of alignment. Now, before alignment, this signal looks like a different, right? But actually, it's a technical variation. You have to align like this. Then you have what? Much nicer separation. Now, is another. This one is warping technique. This one is warping technique. Do you know the concept of calibration? Calibration and warping. Have you heard about the calibration, right? Now, any kind of a machine, you have to calibrate. Calibrate means you decided one signal. Yeah, decide one signal. I calibrate it. Okay, I moved here. Then all the signal should go same degree as much as I did. That's the calibrate. I move all the signal like this one. Warping means warping. W-A-R-P-I-N-G. Warping means independent each signal. Yeah, like this one. I move here. Okay, this signal move the other way. Then we need a mathematical algorithm. Calibration, you don't need a mathematical algorithm. Everything move. But warping case is like each signal you have to do this features. But this kind of warping technique. Now, if you do before alignment, which means now is same signal is a two different things. Now, you don't see any clustering in PCA analysis. But after alignment, very nice. So now this one is advantage of alignment. But also the other way around is possible. Now is here. And normalization. What's the normalization? Then I wrote it down. In the statistic, always normalization we need it. Normalization.
All your features in the same range.
This is scaling it. Scaling normalization sometimes we are confused. Normalization is like a Euler Like let's say give a urine sample. Yesterday I drank some beer. Yeah, then I have a very diluted urine. Yeah. Yesterday I drank any drop of water, very concentrated urine. Yeah. I measured it, very diluted urine and concentrated urine. Signal intensity completely different, right? Like, let's say I take the alanine cases. In the concentrated urine, alanine is huge. Yeah? And then in the diluted urine, very nice. But if you use raw data without any consideration, you think, okay, oh, my alanine variation a lot. So you have to go to the hospital. Here, this is expensive. So that's why now I think it's a first normalization to the internal standard. Now, I measured here. I measured here, like a gas chromatography, yeah, or chromatography. I added internal standard here, yeah, internal standard. All the signal intensity divided by internal standard, yeah, internal standard. Then we can normalize the signal. You understand what I mean? Yeah. Now, for example, now I injected HPLC for GC, I injected 1 microliter. Yeah? But can you guess this one is 1 microliter? Every time? No, it's not possible because at this time I injected, for example, 10 microliter by mistake. This time I injected 1 microliter. Then always same sample 10 microliter signal is very high if you do not consider malnutrition. Now, fortunately, I added internal standard same here, yeah, same height. Then all the signal divided by internal standard, which means it can be comparable. That's the internal standard normalization, right? Then another normalization is internal standard normalization is very easy to understand. Total intensity normalization. For example, now my protocol is I'm using plant extract 30 milligram, right? But can you trust your balance? Sometimes 30 milligram, sometimes 28 milligram, sometimes 20 milligram by this one. But even you add it after extraction, you add it the internal standard, it's already the way the material is completely different one. Then it cannot be normalized, right? And also now I have a diluted urine, yeah, and concentrated urine. You added 1 milligram of internal standard, but still it's cannot comparable. Why? Because you added this one. And also, when you dry the sample, this dry sample is water content is different. Even you weigh 30 milligram, yeah, you dry today very completely. It is 30 milligram dry weight, but you did it last Friday. Now you want to go to the party and get this one. Then it's only 10 milligram. This is a problem. To solve this one is instead of internal standard, I sum up all the signal, and then each signal divided by total intensity. Then gonna work with this. That's the total intensity. Do you understand? Yeah. So that's why this normalization to make the sample variation make it comparable. Which one is good? Usually for the animal or else metabolomics, yeah. Actually, I first start with the total intensity normalization. I think the time. Any question? Tomorrow I continue. Any questions? Today I want to stop here because yesterday I read your face. You are so tired. Exactly 12 o'clock. So always there is a rule. Best lecture, best presentation, keeping calm. That's why. Yes, that's what 12 o'clock. What? Is there any questions? depending on this one. Animal cases, we don't have we are using usually TSP, except for the blood sample, except for so TSP or TSS, certain amount of this one, all the signal divided by is TSP and TSS. Also, internal standard NMR is good for the calibration 0 ppm. So that's why NMR metabolomy, TSP, TSS, two reasons for the quantitation and the second calibration. But LCMS cases, GCMS cases, ideally, 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 yeah, you have to use deuterated compounds. Like as I showed in GCMS, alanine, because alanine everywhere, plants, right? Instead of alanine cases, alanine deuterated alanine. Then even the chromatography is same, yeah, even same, but deuterated mass is different. We can separate this one. And also another one, digital also is commonly used. And second one is alt. And the one case is one internal standard is one, but then HBS case is a couple of internal standards you are adding. Or if you don't want it, total testing sometimes you can use total testing. So depending on the machine, also depending on the sample, there is some guide. Any question?
Sure. I would like to show you a question. Are you going to talk about how to concatenate the signal from the environment to mass and try to create a more use that matrix like they do in Glasgow? I you know, but I have some doubts on this. I don't know.
I don't know. My lecture is not including you mean the identification case, right?
Yes.
But LC, the combined integration of LC, the mass data with the animal data. So for the study, the algorithmic relation, the rest is actually I'm not using it. And also it's not included.
We'll talk about the alignment of the
Why you don't want to join tomorrow? Yes, it's not issue. I can explain right now immediately.
here, top years.
Okay. Any other questions?
There are Professor,
Another question.
another questions of Lucia Pinheiro. About normalization, when the other methods are better than total intensity.
Why didn't she come here, right?
So sorry for my
No,
English.
no, 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 no. It's not your fault. It's Russia's fault. Where is it? Where's her? So she mentioned I said there is no normalization method is better or not. Yeah? But usually you can use as long as you edit the internal standard, you can use data is better. But always my first choice is a total intensity because it's more fingerprinting way is possible. But sometimes another normalization method is like a unit cases. It's like a unit cases you can use one of the signal as an input. For example, here some signal alanine comes out. Yeah? I'm not interested in that. I'm interested compared to alanine. Then I can use the endogenous compound alanine as an internal. That is sometimes it's good. Sometimes it's good. Although like yesterday I drank a lot of beer. Yeah? Yesterday, today I never drank any drop of water. Very concentrated urine and very diluted urine. But if it's divided, diluted alanine, then it can be comparable. That's the situation. That is the endogenous compound, the normalization cases. But which one is better than total intensity? It really depends. But first choice for the classification plans, I think is total intensity will be the first option. I wouldn't say the best, the first option. Russia. Was she satisfied? Princess girl.
I think so.
Okay, in chemistry, today